So good afternoon, everyone, and welcome to the second day of the Geological Society's Climate Symposium. My name is Mary Gagen. I'm a professor of geography at Swansea University, and I'm delighted to be chairing this third session, so the first of the two sessions this afternoon. I'm just going to give a really short recap introduction for anybody who wasn't in the initial session yesterday to hear Dan's intro. Just to give a little bit of background about what this symposium is all about. Back in 2010, the Geological Society produced a statement called Climate Change, Evidence from the Geological Record. And that was to update the 2010 statement with our best information about the latest research. And then in 2019, the Geological Society and the UK Paleoclimate Society jointly convened an expert working group to produce an update to that statement, which was published in the Journal of Geological Society at the end of last year under the title, What the Geological Record Can Tell Us About Our Present and Future Climate. And that statement was structured around 9 targeted questions. And this symposium follows that structure with 9 invited speakers exploring those same questions and giving an opportunity to summarize our understanding in those areas. In addition to our invited speakers, the Geological Society has a commitment to supporting early career scientists. And over these 2 days, we'll hear from 5 early career scientists with shorter flash talks. We've got 2 of those talks this afternoon in the first part of the session. Finally, we then had an open call for abstracts as part of this symposium and had a large number of submissions. And the Society and the committee took the view in the interest of inclusivity to give everybody who had submitted an abstract the opportunity to present their work and their opinions in the form of 1-minute flash presentations and an open poster session. And that session is after the 2 talk sessions today, and the committee would strongly encourage you all to attend those posters and chat with the presenters, and they'll run as breakout rooms for each of the poster sessions. You'll be able to move between to look at the different posters. Another reminder, as was given yesterday as well, just before we get started, to encourage us all to remember that participants and speakers, we're all required to abide by the Society's meeting and events code of conduct at all times. And it is important that we all understand any of us who are violating that code of conduct will be removed from the Zoom event. And yeah, just to say to all of us, it's good for us all to keep in mind not just what questions we ask, but how we ask those questions. And I think we had a really fantastic discussion yesterday. There were loads of really great questions, and I'm looking forward to that again this afternoon. So without further ado, I'm going to move on to introduce our very first speaker of the afternoon, who is Daniela Schmidt. So Dani Schmidt is a professor in paleobiology in the School of Earth Sciences at the University of Bristol, and she's also a member of Bristol's Cabot Institute. Daniela received a Wolfson Merit Award from the Royal Society in 2015. She's a fellow of the Royal Society, a member of the Young Academy of Europe, and is also an IPCC coordinating lead author. And several of the IPCC authors we've got on this session this afternoon deserve a medal for IPCCing through a pandemic. So got lots of interesting opportunities to chat with some lead authors here. Daniela defines her research focuses on understanding the causes and effects of climate change on marine systems. And she's going to be exploring for us today question 5 from the statement, which is, when Earth's temperature changed in the past, what were the impacts? So with that introduction, Dani, I'll hand over to you.
Thank you very much for the introduction. Just to clarify, I'm a fellow of the Royal Society for Biology, not the Royal Society. So I was given the target to talk about the impacts the change in Earth's temperature had in the past. And as we had such lovely examples yesterday, I will focus predominantly on the ecological impacts. The statement said very clearly that there were links between the magnitude and rates of future sea level change in atmospheric CO2, and the geological record supports those. And we heard Mo Raymond's presentation about that yesterday, so I don't want to go into more detail here. We also heard, the statement also talked about the geological record supporting evidence of changes in the hydrological cycle, and I briefly go into one of the examples because it's also one I draw on with regards to the ecological changes. And then lastly, that marine and terrestrial ecosystem changed in response to climate change with implications for global food supplies. So as I said, Mo did a lovely introduction yesterday with regards to the links between CO2 and the links between CO2 and sea level rise. So I don't want to go into much more detail there. We have beautiful sections such as the ones she studied, which have beaches and corals and gives us indication thereof. While here we have tangible relationships and we can put our hands on those changes, it is much harder if we're having a look at changes in hydrology. A range of changes have been suggested, and these go from changes in clay mineralogy, changes in organic biomarkers, and all of these result into this beautiful color pattern you can see on the graph here of regional differences in drying and wetting, which is very much akin to what we are already starting to see in today's climate records, and also regions where we have no change at all. What happens in the ocean is more complex because it has both the impacts of warming, the resulting changes in stratification, the overall warming of the ocean, but it also has changes with regards to the carbonate chemistry of the ocean. So the uptake of CO2 by the ocean results in an acidification of both the surface and the deep ocean. And then on top of that, of course, the ocean can't be seen in isolation, and it will respond to changes in runoff in the hinterland, those changes in the hydrological cycle I mentioned before, which brings a wide range of nutrients, for example, into the system, which change both the coast as well as the open ocean. The increasing stratification limits nutrient reflux, one of the natural systems, and at the same time, a warmer world is projected to be potentially more stormy. I think it's really important to see that climate change is not something which is happening in the future. We already see relationships between the warming of the surface ocean and the distribution of species today. So what you can see here on the left-hand side is a change in temperature around the British Isles, and predominantly focusing here on the North Sea, which shows you the intrusion of warm waters into the North Sea. If you then assess the changes in distribution, in this case, it's a warm, temperate copepod, so a small crustacean, really important stepping stone in our food webs. You can see that a species which was predominantly in the 60s and 70s found in the Bay of Biscay is now changing its entire distribution up into, along with the Gulf Stream towards Norway. And so we already have changes in the distribution of those species. There's a wide range of other things projected, and the question is, do we find any evidence in the geological record that these are real? So do we see, changes in ecosystem shifts, changes in species emergence, in phenology, in biomass and calcification? So there's a wide range of changes projected based on physiological understanding and based on modeling projections. So I'd like to take you to the geological record, and I'd like to do that specifically in a few selected time intervals. Because one of the main things we need to understand is that just a warmer world is not threatening to ecosystems. The warmth in itself is something which species over millions of years will adapt to. And therefore, we can see lovely diverse systems in the Cretaceous, which was so significantly warmer than today. We also need to see that we can't go too far back in time because we want to understand our current ecosystems. And so while here on the right-hand side, you can see an image of a modern reef, and you can see a reconstruction of what we think a Devonian reef looks like. They're both reef structures, but they're clearly fundamentally different. And so I'd like to take you back to first the last deglaciation, so with the melting of the ice. Secondly, to the Pliocene, which is a time interval which had CO2s akin to what we are currently experiencing. And I think Ellen Haywood will go into more detail on that later. And then I'd like to take you back to the Paleocene, Eocene boundary 55 million years ago and what we can learn from that time interval. So one of the main points I'd like to reiterate here is what people have said yesterday as well, is the uniqueness of the current changes in CO2. So what you can see here with age going, in this case, young here, older to the right, what you can see here is the glacial interglacial CO2 records reconstructed from the Greenland ice cores. You can see higher levels in the Holocene, you can see lower values during the glacial periods. The change, if you just average over this time interval, is around 0.02 ppm per year. We, over the last 120 years, have had, again, on average, a change of around 1 ppm per year, so significantly different ranges. And what you can see here is, again, this transition, now this time the other way around. So you have cold here, that's the last glacial at the top, and you have the warm Holocene here at the bottom. The black gives you the indication of the change in oxygen isotopes, which stands for the warming and the ice volume, so it's a combination of both. And the red gives you the weight of this species, Globigerina benoides, which is an important planktic foraminiferal species. While this just looks like 4 ping-pong balls next to each other, they are ubiquitous in the surface ocean, and they're really important with regards to producing carbonates in the open ocean system. And what you can see here is that at times where the CO2 was lower, we had heavy, thick specimens which were weighing around 20 microns. And today, or in the pre-industrial times, we have lighter and thinner specimens. What it also shows you, and that's really important, is that the rate of change overall is quite similar. So what we see here is that if we have gradual changes in CO2, the calcification of this organism is changing, but it is changing within its natural bounds. So there's no risk of concerns of losing this species. Another species will take over in other locations. So let's take me a step further back. Again, let's have a look at calcification because there's so many of the parameters we could have a look at. What you can see here is a record of the Pliocene, CO2 at the top, delta 018, which in this case indicates a growth of the ice volume. And what you can see here is overall values around, let's say, 400 ppm. And then after this time interval here, you can see a drop towards around 300 ppm. What you can see also is that you have very low amplitudes here in the delta 018, so very small changes in the ice volume, then moving over towards significantly larger variations. And we were interested in seeing if we have evidence for changes in the calcification as projected for the future across this change in CO2. The assumption would be higher CO2 would produce less carbonate, lower CO2 would produce, the species would produce more carbonate. We've looked at 2 different groups. These are haptophyte algae, these are coccolithophores. So if you go to the White Cliffs of Dover, you can see that they are rock-forming organisms. So every time you use chalk, you have millions of those. And again, in this case, 3 different species of planktic foraminifera. We looked at 2 different locations because we wanted to see if the tropics, where temperature might become high so that the species might be threatened by it, versus a mid-latitude, which is much more a dynamic environment. And what we can see is that there's different variability between a tropical site and a cold water site, that there's different absolute values between a temperate species and a tropical species. There is no change over time. So again, this relatively low change in CO2, a roughly 120 ppm over, again, roughly 80,000 years, did not impact the calcification of the species negatively. So what then causes the concerns we have with regards to the changes in warming in the fossil record? So I need to take you significantly further back in time, which gives you an indication of quite how unique the current experiment is. And I'm taking you to the Paleocene Eocene thermal maximum, or the PETM. It's the difference to the 2 intervals I described before is the rapidity with which the changes happened and the amplitudes with which these happened. You can see associated with this event changes on land, so we can see changes in vegetation. You can see changes on amongst the animals. It's just by chance, it's the base of the mammals. But you can see very clearly in the geological record that something changed rather dramatically. What you can see in those pictures on the left-hand side are two photographs of a core which records this interval. You can see in white the time before the event, and then you see a very sharp boundary turning towards red, which indicates this change. If we are losing, the color changes because of a change in the carbonate in the sediment. And there are two ways how we can use the carbonate in the sediment. We can reduce the carbonate formed at a specific space, or we can dissolve it after it has been deposited. And you can see the excitement in a much younger me here of finding such a glorious record together with my colleagues on board of the JOIDES resolution, which is one of the workhorses for marine climate research. So what can we see in the record? What you can see here again is now a core picture. So again, you have the whiter, you have the browner, you can see it's less brown towards the top. The dark line here is a core break. Our cores are 1.50 meters long. What you then can see here is time relative to the onset of the event. And you can see two different panels, one of which is carbon isotopes and the other one is calcium carbonate in the sediment. The different colors represent different cores, which we have taken at different water depths between, at that point of deposition, 1,500 meter water depth and 3,500 meter water depth. And I hope what you can see is that these record a very strong change in carbon isotopes, which we interpret as a large injection of carbon into the ocean atmosphere system. There's a gap right at the boundary, and that's because the material is completely dissolved at this site. But we have others where we can look at the transition in much more detail. What you can then see also is that the perturbation in terms of no carbonate is very short-lived in the very shallow waters and much longer-lived in the deep waters, showing that the carbonate compensation depth, the depth at which carbonate is preserved, shoals became shallower with the injection of the carbon and then recovered into first in the shallow sites and then later in the deeper sites. So how do I look in such old material where we've had strong ecological perturbations, but also strong preservation biases into what the calcification record is? And what we do is we take our specimen. They're so small, this is a pipette tip, and you can't see the specimen easily on it. But what we do is we're bringing it to either a benchtop CT scanner, a computer tomography akin to what you might experience in an MRI scan, and our smallest specimen here to the synchrotron, to a particle accelerator. And what it does is it generates those lovely images for us, which allow us to reconstruct the development of those species. So they start by growing the first chamber and then adding those, as well as its wall thickness, and making those reconstructions you can see here in green. We can then go back and look at the developmental history, but that's not what I'm trying to focus on here. But it would allow us to have a look at changes to that. What I will be presenting here is data which we gather if we take cross sections through the specimen and we calculate its volume and we calculate the amount of calcite. The beauty of that is that we can work with material which has some indications of dissolution, but also some infilling, because painfully, Manzoro Adebawola, whose PhD I'm presenting here, is cleaning up those images to make those reconstructions. And we then calculate its overall size, the surface area, the volume, and the ratio of calcite to volume, to have a look at, is the surface area increasing, which is the area over which the species can forage? Is the volume decreasing because it doesn't get enough food to sustain itself? Or maybe not enough carbonate to calcify? We're looking at the calcification to volume, the calcite to volume, to then understand if there has been a negative impact of this event on the ability of the species to calcify. What is quite important about this event is that it's a really important extinction event amongst this group, the benthic foraminifera. This is a very, very sturdy group. Through the Cretaceous-Paleogene boundary, when the dinosaurs went extinct, there's hardly any perturbation in their diversities or the number of species. But here at this event, we're losing around 40% of the species. The other thing you can see, again, you have the core image here at the left-hand side. You have carbon isotopes indicating where the event is. You have oxygen isotopes, which give you a first indication of temperature. And you have images here of those specimens from the same slide I showed you earlier, Wolfers Ridge. These are all at the same scale. So the most dramatic change you can see here is that we're going from a really, really large specimen to something which is so tiny and still small when we're going to the recovery of the event. A similar pattern of dwarfism is also something which we can see in planktic foraminifer, but I'm trying to concentrate on one group here because of the time. So we're looking at 3 sites. So we have one site here, 690, which is off Antarctica, which is a relatively deep in the ocean. There's the middle panel. We have another site, site 1135, which again is off Antarctica, but very shallow. And food availability for species in the deep ocean changes with more in the shallow water and less in the deeper parts. And then we have a third site here in the middle of the Pacific, a highly stratified part of the ocean where food is nearly absent. And what you can see here is that this is before the event, within the event, in the recovery, and after, going from left to right, always in the same colors across the 3, and the cross section underneath. What you can see here is that at 1135, despite the fact that all 3 sites have the same degree of warming, they're in the same bottom water mass, this site shows no change at all in calcification. Again, as percent calcite, as I explained earlier. While the difference here with a neighboring site in the Southern Ocean, but deeper, has a reduction in calcite production by this species during the event, and then a recovery towards the values before. What we can see at the site in the Pacific is that we have really high variability, but overall, again, no significant change. And so this suggests that there are other factors than warming which influence the carbonate production by this species. It also suggests that the water depth is really important, because with 2 sites which are at a similar latitude, we see that the deeper side has a reduction in calcite production and the shallower one does not. So the next thing we did then with those specimens is to have a look if we can see changes in its form. So are they becoming smaller? Are they changing its form? So again, this is the same arrangement, the same cores in the same order, this time showing you the surface area to volume ratios, and images again at the bottom trying to highlight that. These images are all at the same scale, so I hope that you can see very clearly at both site 1135, so the both Southern Ocean site and site 690, that the specimens which have grown during the peak of the carbon isotope excursion are much smaller. While in the tropical Pacific, they were small from the beginning. So they must have already been limited in their growth, and they've never reached sizes as you would have at these other locations. If we then look at those 3 sites, again, we don't have dramatic changes in the surface area to volume, so the ability to forage over the amount of biomass it needs to support at size 1135. There is some increase, but it's not statistically significant. In contrast, at 690, we see a dramatic increase of that. So it changes its shape. And if you interpret the importance of surface area in terms of foraging or in terms of oxygen uptake, you could interpret this as a need to have more food to sustain calcification and to sustain its metabolism, so its ability to function. So we see both dwarfism and shape changes in this species. We've tried for the last IPCC assessment to summarize some of those events and to compare between the PETM and the current. And there's some things which give us confidence that we understand those patterns very well. So what you see here, for example, is a warm water species migrating into the Southern Ocean. This is the increase of a warm water species in a cold setting today. Different taxa, but ultimately what they both do is species in the open ocean follow their temperature optimum. So they just change their biography. They've done it then, they're doing it now. And it relates back to the example I showed you at the beginning. In the geological record, we've had extinction, and currently there's no evidence yet for extinction in the ocean. There are clearly extinctions on land, but they are predominantly driven by land use changes up to this point and not by climate change. And then calcification, I showed you lots of different responses at different locations, and the same is something you can see today. These are coralline algae at 2 different locations, and they do different things. And these are tropical corals, and again, they do different things. So calcification seems to be something which is much more dependent on its species and its own metabolism. What is most important, though, is what I was trying to get to you earlier on, is the difference in time. So the CO2 rise we've had since the beginning of the industrialization happened over 120 years. And therefore the changes here in warming and in atmospheric CO2 are incredibly quick compared to an event. In this case, this time is in millions of years. And so we've had an onset over several thousands of years of a similar amount of carbon than what's projected to be emitted because of fossil fuels and land use changes. And so what's absolutely clear is that we can see changes in the geological record of species shifts, and that these has happened at rates which were significantly lower than what we are currently seeing. We know that rate of change determines an organism's ability to acclimatize or to evolve if needed. And therefore, there's severe concerns of the impacts this will have with this incredibly rapid change. There's a large number of climate change impacts which are already detected. And there are changes in the hydrological cycle, there are changes in fire regimes, there are changes in where species are growing and how they're migrating. The question is, and what we are supposed to do with regards to future projections of how do we upscale from the knowledge we have at individual places and on individual taxa? We know that burning fossil fuel increases CO2. If it increases CO2, we also know it lowers the pH because that's a simple equilibrium equation. Indirectly, it changes, makes the planet warmer, it changes stratification and oxygen loss. We have experiments which show us changes in growth and development and reproduction of individual species. But ultimately, what we are interested in is ecosystem services, such ability to produce food, ability to regulate CO2, and the loss of species for us. And we have increasing uncertainty when it comes to those projections. The other thing which is still very unclear is, a lot of people are saying that the impacts aren't visible yet across many of those systems. We have a lot of natural variability, and this is just the hypothetical, decadal variability, which we see in many parts of the world, interconnected, teleconnected with each other. So the question is, can we wait until the anthropogenic climate change has left this envelope, or are we significantly concerned about the projections that action is happening now? Ultimately, we know that species followed and will do so in the future, their temperature optima, and they move towards the pole and they move up the mountains. And mountains end eventually and poles get warmer. That we have extreme events and compound events of warming and acidification and oxygen depletion, and that in the past these resulted in extinction and loss of ecosystem services. We know we have evidence for this across all continents and across all oceans. We know that in history people have always coped with climate variability and extremes, but it has never been as fast as it is currently. And so we need to have a decision if we want to have action despite uncertainty about the severity and the timing of those impacts. Thank you very much.
Thanks so much, Danny. Really fascinating, and it's always amazing to see those timelines next to each other. We've got some great questions, and I would encourage you all to keep posting your questions. And just to say to early career researchers who are on the webinar, please don't be shy. We were very, very keen to hear from you. So Danny, I'm going to start with some of the more general questions that have been posted, if that's okay. We've got a few questions around ocean acidification and whether future predictions take into account elements of ocean chemistry, such as buffering effects. I wonder if you could talk to that for a moment.
Yeah, I mean, the buffering effect is beautifully visible in the paleo example, because what happened there is that the deep ocean sediments dissolved and therefore buffered the impacts. That process takes around the time of the turnover time of the ocean. So we're talking about 1,000 years. So it's the question if we have that time. I've also seen another question which talks about the term ocean acidification in itself and asks, you know, if the ocean will ever become acidic. And it's like, no, it won't. We're still talking about global warming, and Britain will nearly never be hot. And still we're talking about the change, the relative change. And so acidification just talks about the move away from the basic 8.1, which we've had pre-industrial.
Great, thank you. Thanks so much. There's a question as well about how long some of the species that are in the oceans have been around, that I guess I would summarize as if a species has remained largely unchanged for hundreds of millions of years, does that mean it's immune to changes that happen over timescales of decades or 100 years?
So that's hard to say. In general, what we see is that species which are very specialized, so which live in a narrow geographic area, are those who are more vulnerable. So those which have long time ranges and those which have long geographic, wide geographic coverages tend to be more stable, because if they find environments at one location which aren't suitable for them anymore, they can move to another. While if you're highly specialized to one place, that next space doesn't exist. And so we tend to describe it more in terms of the specialization of an organism.
Thanks so much. There's a few people asking as well about the variety of impacts that are on oceans at the moment, things like overfishing and all the kind of ecological and human effects as well versus climate change. So would you say that in our modern oceans, the current changes that we're seeing are mainly driven by climate change, or those other human effects, overfishing and those sorts of things?
So if we're looking at a coastal system like the UK, we can see that, you know, changes in land use change the runoff into our coastal systems, brings in more nutrients, brings in more sediments, and therefore is impacting there strongly. If people talk about fishing, that system is very clearly threatened because of the overfishing and not because of climate change. If we're going to the open ocean, those pressures become smaller, and therefore the impacts of climate change are significantly easier to detect, because those other secondary drivers are less important. But in a coastal system, you can also turn this around and say, you know, we have the power to change things and reduce some of the stresses which, additional to climate change, impact those systems, because land use changes, pollution, you know, of nutrients, of plastics is in our hand. And so it gives us ability to take charge and change things and not wait for global decisions.
The all important decisions being with us. So there's a question around the warmest seas, and that there's a sense, someone's saying they've read that the world's warmest sea, the Coral Sea, is actually the healthiest. Could you talk about that?
So it's a biodiversity hotspot. So it is a place where a lot of species have been living for a long time. And because it is relatively warm today, and lots of those species are reaching the upper levels of their temperature ranges, it is a much more vulnerable place. So you can have a very healthy place if there has been very little human interaction, which is now very vulnerable because the species are at the upper edge of their temperature ranges.
Okay. I'm keeping my eye on the clock, and we are shockingly on time. So I'm going to just wrap up with one question, if that's okay, and then we'll stay on time. And sorry, I'm just scrolling through questions here to try and make sure I'm spotting everything. Okay, I think we've covered some of those. I wanted to ask you, Daniela, actually, if I could, about connectivity in the ocean. So when I talk to marine NGOs, this is a really hot topic for them, the idea of how source areas and connectivity is really important for species health. So a herring spawning ground is essential for the survival of that species. And I always think it's really interesting to think about how climate science can kind of address those questions that are vital for the NGOs that are trying to manage environments now. And is there anything that the geological record do you see evidence of changes in connectivity in the past from the geological record?
So if we take the example again of the Paleocene thermal maximum, we saw species which have never been seen in high latitude suddenly moving into those regions. So if we have such dramatic changes in the distribution, we also need to think about that today our approach of those NGOs is to protect marine protected areas. If marine protected areas, though, are static and are not changing with the distribution of those species changing, so that's the connectivity they talked about, then they become not fit for purpose when we already see relocation of species over the last decades. And so that's something which, again, is really powerful for us to think about, how we could improve some of the threats, to reduce some of the threats to species, is by having protected areas which allow those stepping stones where, the breeding grounds, the adult species, or, relocation of species further to the north. In the UK, we are in the transitional zone between two climate zones. And so you can see those changes along our coast really rapidly. But it also allows us to provide those stepping stones for species.
Thanks so much, Danny. Really, really fascinating start to this session. Many thanks. I'm going to stay nicely on time and move on to the first of our flash talks from the first of our early career researchers for this afternoon. And it's my pleasure to introduce Rachael Brown to you. Rachael is a third-year PhD student with Gavin Foster at the University of Southampton. And her work looks at boron isotopes and using them to reconstruct past CO2 and look at investigating the role of CO2 in relation to the major climate transitions, such as the intensification of Northern Hemisphere glaciation and late Miocene cooling. And she's going to be talking about Miocene CO2 in her talk now. So I'll hand over to you, Rachael. Thank you.
Okay. You can see it?
We're good, yeah, go for it, Rachael, thank you.
Okay. Hi. Yeah, so today I'm going to be talking to you about late Miocene climate and the role of and its relationship with CO2. Thank you to all those people for helping me with all this, and these people for paying my rent. So first things first, why do we care so much about CO2? Well, it's a really powerful greenhouse gas that is able to trap heat in the atmosphere. You increase the amount of CO2 in the atmosphere, you increase the amount of heat trapped, and that results in warming. However, this relationship is modulated by internal climate feedbacks and boundary conditions. As a result, there's uncertainty in regards to what the expected temperature change is for any given change in CO2. Therefore, one way to reduce this uncertainty is to look at the relationship between CO2 and climate in the past. The majority of studies that have done this previously have focused on periods that are much colder and primarily the late Pleistocene. The problem with these in regards to constraining future warming is that they're one, colder, and also they have really large ice sheets, which were going to be both warmer and have no ice sheets in the future. So given that there's potential for state dependency of climate sensitivity, we should probably also try to look at the relationships between CO2 and climate in warmer than present climate, past climates. Enter the late Miocene. The late Miocene is a really good time period to target for these kinds of studies, mainly because it is one, warmer than present, and two, the arrangement of the continents is similar to that of today, so it has similar boundary conditions. It's also a period of intense climate change, given that there was substantial global cooling, there was likely the beginnings of the buildup of ice sheets in the Northern Hemisphere, there were substantial changes in the carbon cycle and global vegetation, to name but a few. However, in spite of all these changes in global climates, the CO2 record is rather ambiguous, showing not a lot of change in CO2. This has led to the suggestion that changes in CO2 were actually decoupled from changes in global climate during the late Miocene. However, a lot of these records are, one, associated with some pretty large errors that make it difficult to resolve these changes in CO2, And also, a lot of these records are really low resolution, meaning that we may be aliasing any of these changes in CO2. As such, we decided we wanted to create a high resolution record to resolve these changes in CO2 during the late Miocene, particularly during this period, when during the temperature minimum of the late Miocene from 5 to 7 million years ago. We were able to do this using boron isotopes. Now, boron isotopes are able to really accurately reconstruct changes in CO2 and the radiative forcing associated with it. We're able to do this by first looking at the ratio of the stable isotopes in little surface-dwelling plankton called foraminifera. Now, the change in the boron isotopes of these little forams is directly related to changes in surface ocean pH. Now, because changes in still hear me? Because changes in surface ocean pH are directly correlated with changes in atmospheric CO2, we can use the relative changes in boron isotopes recorded in these forams to reconstruct changes in CO2. So, what did we find for the late Miocene? Well, in regards to, we found that there was about a 0.5 watts per meter squared reduction in forcing associated with CO2 during the late Miocene, but we also probably more notably observe of 2 watts per meter squared reduction in radiative forcing associated with CO2 from about 6.3 to 5.9 million years ago. This corresponds with all the previously mentioned changes in global climate observed during the late Miocene, the global cooling minimum, the expansion of ice sheets in the northern hemisphere, carbon changes in vegetation, all of them. As a result, our record strongly implies that, contrary to previous suggestions, CO2 and climate were coupled during the late Miocene. So, we have a record of the radiative forcing from CO2 and global mean surface temperature change. Next stop is to calculate climate sensitivity. So, a quick reminder about all the different climate sensitivity definitions that von der Heydt talked about really nicely yesterday. Earth system sensitivity is the temperature change in response to a doubling of CO2, accounting for fast and slow climate feedbacks. Equilibrium climate sensitivity only accounts for fast climate feedbacks, i.e. changes in clouds, while Earth system sensitivity will also account for changes in land ice sheets and carbon cycle changes. So, we estimate that equilibrium climate sensitivity or Earth system sensitivity for the late Miocene to be about 9.3 degrees warming per doubling of CO2. This is really similar to that observed during the late Pleistocene, which is between 7 and 13 degrees warming per doubling of CO2. This strongly implies that strong slow climate feedbacks were operating during the late Miocene, similar to the late Pleistocene. Indeed, various model simulations for the late Miocene climate suggest that high sensitivity was due to some land ice albedo effects and differences in global vegetation cover. To calculate equilibrium climate sensitivity from this, given that we don't actually have direct proxy measurements for the radiative forcing associated with albedo feedbacks from vegetation or ice sheets, we look at the ratio between equilibrium climate sensitivity and Earth system sensitivity in a suite of various models and use that to parameterize slow climate feedbacks. Using this method, we're able to estimate equilibrium climate sensitivity for the late Miocene to be about 3.9 degrees plus or minus 0.6 per doubling of CO2. This is well within the range given by the IPCC of 1.5 to 4.5 degrees, and strongly suggests that we don't actually see any state dependency in regards to warm climates with equilibrium climate sensitivity. This is not to say that there isn't any state dependency, just that we currently don't see any in our data as it currently is. So, to conclude, CO2 and climate were strongly coupled during the late Miocene, contrary to previous assertions. And the high Earth system sensitivity observed is likely due to strong, slow climate feedbacks, such as ice sheet albedo, ice sheet, and different coverage and vegetation albedo feedbacks. And when we take into account these slow feedbacks, we get an equilibrium climate sensitivity that is, for the late Miocene, that is within range of recent estimates. Thank you.
Thanks so much, Rachel. Whistle-stop tour through the Miocene there. Just to keep us on track, I'm just going to ask one or possibly two very quick questions, if that's okay. So first of all, can I ask you to talk a little bit about what we think has caused these changes in Miocene CO2? Do we think they were weathering changes that dominated, or volcanic, or a combination of the two?
No one really knows. There were a lot of changes in the carbon cycle during this period, particularly with in regards to, like, there was the carbonate crash where a lot of carbonates just started dissolving for a bit, and there's a drastic shift in the vegetation on in the terrestrial realm. So there is suggestion that potentially there was a shift in where the carbon was stored into the deep oceans. So that might be it, but we don't really have good enough records at the moment to resolve what might have been the mechanism for the CO2 reduction.
That's always a good one then. If you're starting out on your work, you've got something for the future, an unanswered question. One other question, someone's asked, with regards to Miocene ice feedbacks, were they mostly related to Northern Hemisphere or Southern Hemisphere ice sheets, or again, is that something that's in progress?
That is something that we don't know. There was growth in both the Antarctica at this time was also growing, as well as there was an increase in sea ice and ice in, like, the Northern Hemisphere. So both probably contributed, most likely.
Thanks so much, Rachel. Really, really fascinating talk there. Thank you for one of our flash talks. And we're going to move on now, more or less exactly on time, proud to say. Thank you so much to our speakers so far for sticking to time. So our next invited speaker is Alan Haywood. Alan is Professor of Paleoclimate Modelling in Leeds in the School of Earth and Environment. Alan was PDRA within meteorology at the University of Reading, and then moved to BAS, the British Antarctic Survey, where he directed a 5-year research programme on the greenhouse to icehouse transition within Antarctica. Since joining Leeds, Alan has helped to lead the International Pliocene Model into Comparison project, and he contributed to both the 5th and the 6th assessment reports. Alan's going to talk to the 7th question in the climate statement, which is, are there past climate analogues for the future? So I'll hand over to you, Alan.
Okay, thank you. Thank you, Mary. Okay, can you see that okay?
Yeah, that's great, Alan, thanks.
Okay, thanks very much. So let me start by saying thank you for the invitation to contribute to this event. I was fortunate enough to be involved in helping put together the first position statement on climate change, which was done by the Geological Society some years ago. So it's great to be back to contribute again to this active area, an important area of science. So I have a particular question that I'm addressing today, which is, are there past climate analogues for the future? And before I go into it, I would just like to point out the contribution of my PhD student to this talk, Lauren Burton. Lauren is a first-year PhD student who's already really doing very well and producing a lot of great science. And as I was putting this talk together, it became more obvious that I needed more of her input. So I'm sure you'll be hearing more from Lauren in the future. So I'm just going to cover what I'm going to be presenting today. So I want to start from the basics and talk about the definition of analog and what we mean by climate analog. Then I'd like to go on and talk about why do we search for analogs as scientists, as geologists, as paleoclimatologists. Then go on and talk about the types of analog that we can find and provide some examples of their usage. And specifically in this context, I want to touch upon three different types of analog. The question about whether or not there is a true or perfect analog in the geological record for what's going on right now, the partial analog or the process analog. So we're going to take each one of those in turn with some examples. And then I'd like to go on and talk about some wider considerations on application and use of analogues, and then kind of try to tie things up at the end with some comments and some things which I will hope will provide some food for further thought. So let's start off with the definition of analog and climate analog. So the Oxford English Dictionary, the noun analog is a person or thing seen as comparable to another. Climate analog has been described in the literature something along the lines of this: two sites that share a similar climatic conditions. The two sites may be separated geographically and or temporally, i.e. similar climatic conditions experienced at different periods of time as climatic conditions change and migrate. So how do we transfer that in the context of paleoclimate? And I'm trying to do that here, essentially an interval in Earth history that shares similar climate conditions and characteristics to model simulations of future climate change. And of course, we can extend that also to a paleoenvironmental analog, similar environmental conditions and characteristics. I mean, and this is obviously a key area, a very active area of research. One of the things I like to do to try to demonstrate this is go and have a look at the published articles that are out there and do a kind of a meta-analysis of how much is coming out over time. So I did quite a conservative search here, looking at the different topics, paleo, analog or paleoclimate, and restricting that just to looking at the areas of meteorology and atmospheric science. And I found over 1,000 publications which have those keywords, which from the year 2000, and it's been rising rapidly every year since the year 2000. If I then extend that to the geosciences, then we end up with something like 23,000 articles. So clearly, this is a very active and ongoing question and area of research. So why do we search for analogues? Well, I think the best way to try to answer that is to touch base and reflect upon probably the two primary themes that we have in paleoclimate research. The first being the kind of past for past approach. So we want to understand the complex nature of our planet's climate and environmental evolution. So how did we get to where we are today? There's another primary theme, past for future, and this really focuses around the fact that we want to apply the knowledge about the understanding of the past climate system to try to address major science issues facing society, so climate change. So what can the past tell us about our future? So analogues really reflect our willingness to play our part in addressing global change and the uncertainties in knowing our future. But critically, they also help put the current climate change into a broader geological perspective. And I think that's something which is incredibly useful. So on the right here, I'm showing you an outcome of a collaboration that we had at Leeds with an artist, James McKay. And we at the Leeds group, we do a lot of work on Pliocene research. And we decided, wouldn't it be great if we could try to kind of synthesize all of the information that we had from the paleontological record, from the geological record, from climate models, and from ice sheet modeling that's been done for the Pliocene to try to come up with a composite picture of what we thought the environment was like on Greenland during the mid-Pliocene, so around about 3 million years ago, as a way to try to convey that information about how much the environment and climate had changed, how much it was different back then, to a broader audience of people. And so the obvious question that comes out when you look at something like this is this a picture which looks something like Greenland's future? So let's talk about the types of analog and talk about some examples of their use. So let's touch upon the first one, the concept of a true or perfect analog. So what I mean there really is that there's an interval in Earth history which faithfully and precisely records a climate perturbation that's identical in its cause, magnitude, rate of change, and with identical at a time where there's identical sensitivity of the Earth system to forcing to a future climate state. And I think one of the things that we can do is that we can understand that that's an extremely difficult question and an extremely unlikely outcome. And there are a number of reasons for that. So the first thing is that we are living, as some say, we are living in the Anthropocene epoch. So in terms of the climate changes that have occurred in the past, of course, they occurred in the absence of us in our species. Now, we have an absolutely fundamental role in the changes which are going on right now in our climate system across the world. But I think the key thing is that it's not just the climate that we're forcing directly through greenhouse gas emissions. We're having a fundamental effect on our planet as a whole, which the whole concept of the Anthropocene tries to highlight or codify, exemplify, if you like. And I think the thing that we also have to appreciate as the time goes on into the future, we are hardly going to be passive bystanders in what the outcome finally is. So merely from that point, the fact that we are here and we have had a role in this makes it very unlikely to be able to find something which is exactly equivalent, which will be exactly equivalent in the context of the past. But even so, if we just go beyond that just a moment to think about some of the other reasons, and it's kind of nicely laid out in the journal's publication, the Lear et al. Publication here. But if we think about some of the rates of change, so modern CO2 emission rates extrapolated to a PTM timescale are something like 9 to 10 times higher than the PTM rates. So it's actually requires some considerable thought to relate the timescales in which things have happened into the past to compare them to the rates in which things are happening now. So we know that there's a difference in the rate of CO2 emission, even for something like the PTM, which was pretty rapid by geological standards. If we think about the rate of global temperature change, even for something like the last deglaciation, and we saw very rapid changes, they're slower. They were slower than the current rates of change by some considerable margin. But then we can look at other aspects of the Earth system response to forcing and to greenhouse gas forcing like sea level, and we can actually find other examples in the geological past where the rates of change may well have been considerably faster than we're currently observing. So there is an issue associated with the rates of change. And of course, as other speakers have highlighted in their talks, the rate of change is critical in correctly assessing the impact and the ability of our planet to deal with what's happening. The other thing is obviously a lot has changed over geological time. And the further that you go back into the past, the higher the potential is for those changes to become larger and larger. And this has an impact even on thinking about the degree to which the basic state of the climate system and the sensitivity of the climate system to forcing and to greenhouse gas forcing has evolved over time. So I'm showing you a picture here of a Cretaceous paleogeography, and I'm underneath that showing you a reconstruction of the northern hemisphere, North America during the last glaciation. And so clearly, these differences that we've had in the past in the environmental conditions, the base state, the environmental condition is rather large. And Anna did a great job yesterday of articulating how the point at which you start from can have an impact on how the climate responds to a greenhouse gas change and a radiative forcing. So the fact that the Earth has changed its probably sensitivity over time is important in the context of considering the idea of there being a perfect analog in the geological past. So if we just put that aside for a moment and think, well, we can't find a perfect analog, are there partial or imperfect analogues that we can look at? And so I'm defining that here as an interval or event in Earth history that has a sufficiently similar climate to model simulations of the future to enable a meaningful comparison and to derive meaningful insights in terms of climate signals as well as rates of change. And there has been some work there's been a lot of work which has looked at that, and I'm showing you one particular example here by Burke et al. In 2018, published in Proceedings of the National Academy of Sciences. So what happened here was the authors took different simulations produced by 3 different climate models: the GISS model, the Hadley Center model version 3, and the NCAR model, CCSM, for different potential geohistorical analogues. So that would include the Eocene, the Pliocene, the last interglacial or the Lig, the Holocene, the historical period, as well as a pre-industrial baseline, and then actually performed a statistical comparison looking at the similarity between those model simulations for those different geohistorical analogues compared to different scenarios for future climate change. And I'm showing you here two of those examples. So the concentration pathway 8.5 as well as 4.5. And so this is essentially showing you, the top figures are showing you the kind of 3 multi-model mean outcomes for that, and the degree of similarity that we see between the future climate scenarios 8.5 and 4.5 and the different geohistorical potential analogues that we're looking at here. And so we can see that actually the degree of fit is partly dependent upon which RCP scenario we're actually going to follow by the time you get out to 2250, 2300. But you can see, so for example, for RCP 4.5, that in terms of the degree of fit, then the Pliocene rapidly into the near future becomes the one which has the greatest similarity. If we follow RCP, something more like RCP 8.5, then the Pliocene starts off by being the most analogous, but then by around 2150 or so gets overtaken by the Eocene. Now, obviously, there are differences from model to model in that, but overall the patterns are actually quite similar. So we can kind of see that we can actually relate patterns of change that we're able to simulate or reconstruct into the past into things which we anticipate as possibilities for the future. But I mean, one thing I suppose I would note is, even in the context of RCP 4.5 and the Pliocene, we're getting up to about a 37% similarity. Perhaps that is sufficient to say it is a good partial analog, but no one's actually defined the threshold at which we can actually say that. I'm going to come back to that in a little while. So you can look at this in another way if you like. So this figure that I showed you here previously is now being represented here on the left for RCP 8.5, but it's showing you the spatial evolution of that similarity over the world. So we start off at 2020 to 2050 and go down to 2200. So you can see lots of blue. As we continue to go forward in time, then we start to see that more and more parts of the world become more Pliocene-like and more Eocene-like. But I think one of the other things we also see here is that we move into scenarios into the future where we get an increasing area of the world which is really doesn't have a geological analog, at least in terms of the different ones that we sampled here, which is quite breathtaking in that sense. But as I said before, there are different things which contribute to climate changes of the past, and I think one of the things which is quite useful for us to try to understand is the overall influence of carbon dioxide on patterns of climate change that we have seen in the past. And this is certainly one thing that you can try to address using climate models, which do a whole series of different experiments, making incremental changes in the boundary conditions within those models, so that you can actually identify the contribution from individual changes that you make to the model. And I'm showing you here an example for the Pliocene. This is an influence map showing you for our own model, HAD-CM3, how important, what sort of level of influence the forcing of carbon dioxide had on the amount of temperature change that the model simulates for this period, so the Pliocene minus the pre-industrial. And I think one of the things you can see is that over wide swathes of the world, then CO2 the CO2 forcing is having a considerable to dominant effect on the pattern of change that we see at this particular time. And that really backs up, I think, one of the things that Paul Valdez was showing in his presentation yesterday when he was showing that for multiple time series. But one of the things which is clear to and important to remember is that climate is not just temperature. We talk about temperature a lot in the context of the paleo because it's one of the key things that we can try to reconstruct geologically. But temperature is only one aspect of climate. So I'm showing you here on the top left another example of the figure I just showed you, but this time for precipitation, not for temperature change. And here we have quite a different outcome. So again, there are areas of the world in the context of the Pliocene where the CO2 forcing is very important in determining the pattern and the magnitude of precipitation change. But actually, there are large areas of the world where the response of CO2 in terms of the precipitation change we see at this point in Earth history is relatively small. And so what that's actually suggesting here is that the other boundary condition changes that we've made in the model, principally changes to orography and to ice sheets and to vegetation, is having more of a dominant effect in determining what happens to precipitation than the CO2 forcing. And I'm showing you something here which is similar in the context of sea surface temperatures. And here this is more of a similar pattern to the pattern and the influence plots associated with surface air temperature change. So we're able to do this using models. And of course, we have access to different model simulations which have performed the same experiments. So we can also assess how dependent these kind of results are based on the model that you use. More challenging is to try to do this sort of analysis from the point of view of proxy data alone, although if there's one thing that I've learned is you should never underestimate the innovative capacity of geologists and paleoenvironmental scientists. So let's move on and think about other types of analog examples. So I want to just talk about here the deglaciation, and I'm moving away from the partial analog and really moving now into the kind of process analog space. So we're not trying here to sort of directly relate patterns of temperature and environmental changes to past and the future. We're trying to actually understand the fundamental processes which are operating at the time, which may be which were key and may be relevant in the context of the future. So we're going to take three examples here, going progressively further back in time. So this is the first one, the deglacial period. So we're now talking about a time where insolation changes in insolation forcing and CO2 forcing over time had really an absolutely profound effect on global climate and on the amount of ice which was in the system at this time, particularly in the Northern Hemisphere, and the growth and decay of the major ice sheets, including North America. And I'm showing you here a study by Laurent Gregoire et al., which was published back in 2012. But essentially, what this study, one of the key outcomes of this study was the fact that we can kind of understand the patterns that we see going through the deglaciation by understanding the complexity associated with ice sheet morphology, geomorphology, the underlying topography at that time, the interrelationship between that and the forcings that were going on at that time, and how we can see sudden accelerations in ice sheet loss and also then sea level rise because of surface mass balance feedbacks and mechanisms called something like which were referred to as the saddle collapse. So suddenly the fact that you had an ice sheet which was made up of multiple ice caps, which then decayed and separated with the resulting acceleration of ice loss and therefore sea level rise. And so we're able to then think about the context of which mechanisms like that may relate and may be relevant in the context of the future. Similarly, if we go back and talk about the Pliocene, one of the key things we want to know and are focused on is actually what happens to atmospheric circulation at this time. So I'm showing you here a study by Sun et al. 2013, which did an analysis of the major components of atmospheric circulation. And the thing that they were pointing out was that they were comparing the Pliocene simulations of the Hadley circulation to also a specific scenario for climate change into the future. And you don't have to be an expert in analysing atmospheric circulation plots to be able to see the strong similarity between these two plots down here at the bottom of this figure. So clearly there are some fundamental things that we can learn about the nature in which first order effects like changes in tropical to high latitude temperature gradients, the way that influences large scale atmospheric circulation in the past and also into the future. The last one I want to talk about is in the context of the Eocene, and this was a paper that came out back in 2018, which did, I think, a really interesting job of compiling different atmospheric CO2 records for this particular time and coming up with a compilation of tropical sea surface temperatures as well as deep ocean temperatures. And one of the things that they found from this was that tropical and deep ocean temperatures appeared to change in parallel. They made the argument here that this was consistent with greenhouse gas forcing being a primary driver for Eocene climate change, but that there was a strong linear relationship between the tropical and deep ocean temperatures. And the interesting thing about this was that it sort of implied a constant polar amplification factor throughout a generally ice-free Eocene. So certainly, even though things back in the Eocene were substantially different compared to they are today, and that we would expect in the near future, there are still fundamental things about the way that the system operates, which can be translatable and referable from the geological past into the future. So let's just move on in terms of thinking about some of the wider considerations on application and use. And I think some of the key things that we need to consider are outlined here. So I think when we talk about this, it's important that we define what we mean by climate analog. If we're going to do more of this, and I'm sure we will, it's important for us to be explicit in those studies about what we actually mean. And I think the key thing is that climate is not just temperature. So we have to be more specific in how we refer to these things. So in reality, we often examine a single component of climate. Are we talking about an analog of temperature, an analog of precipitation, or an analog of climate? And if it's climate, it requires us to think a bit more broadly. We certainly appreciate that many things have changed in the past that can alter climate, but these are not necessarily always relevant in the context of the future. And we can do the kind of studies that I've showed you to try to get an idea about the degree to which greenhouse gas forcing is influencing specific and critical regional changes in climate and environments in the past. And we can do that with models, and of course, but it's a greater challenge using proxy data. It's a mistake just to focus on intervals of the past that had greenhouse gas forcing related as being linked to the changes that were going on at the time. There are other periods of time which were forced by different types of changes, and so insulation, for example, which were still led to regional and seasonal changes which might be similar to what we expect for the future, so that we can still learn from these many intervals, and they remain valuable, particularly from the point of view, I think, of process analog studies. So we've done a lot, we can do better, and I think what we can do moving forward is to continue the pattern of development that we're already doing around more systematic and quantified approach. So I'm just going to finish off now by talking a little bit about food for thought. So one thing I'd say in the context of formalized analog studies, I think that one thing we need to do is to clarify what we mean by the future. So as you can see, that was done in the context of the Berkefeld study using different scenarios. So when we say future climate, what do we actually mean? Do we mean 2100? Do we mean 2300? What scenarios of forcing are we going to use along those different pathways? So that needs to be considered quite carefully. And we also need to clarify what we mean by the past and incorporate uncertainty associated with paleoclimate reconstructions and modeling into analog studies. So, for us, if you say something like the Pliocene is an analog for the future, I actually know that we know that the Pliocene actually represents a whole load of different climate states. So one of the things that we could also do to try to firm this up and put a more structured framework into it into the future is to be more precise in terms of what we mean about the past. I think there's some further work to do to define reasonable lower limits of similarity for climate analogues. And I'm not trying to suggest that this work isn't going on. I think that this is work that is already absolutely going on. And I picked up a paper here by Walther et al. In 2019, which was presenting a new method to identify robust, what they referred to as robust climate analogues in climate research. So there they were using a clustering approach in climate space analysis, leading to the identification of what they referred to as robust climate analogues, using upper and lower bounds of future projections. But we can also, in the context of our work, also start to think about how we include the upper and lower bounds of paleoclimate estimates, both from models and proxies as well. And finally, I think the last thing I want to say, which will hopefully lead on nicely to Rachel's talk a little bit later on, and I think what Mo Ramo said yesterday about the importance of co-production and the absolute requirement to continue to develop the tools and techniques to get our work out to the widest possible audience if it's going to have the biggest possible impact. So I think we need to continue to develop tools and techniques and strategies that help us translate this knowledge from the paleo to a wider audience and maximize the potential it can have in helping society deal with this huge challenge that we're currently facing. And I think with that, I'll end. Thank you very much.
Thanks so much, Alan. We've got a few questions, and I've got my eye on the time slightly, but I'm certainly going to ask a couple. So we've got a question from Babette, first of all, Alan. So under a business as usual scenario, Babette saying we are looking at similar rates of changes during the Eocene and asking what could this mean for our future climate?
Sorry, the question was, what does that mean in the context? So
what would that mean if we were looking at similar rates of change as experienced during the Eocene? What would that future climate look like?
I think, I don't really quite understand the question because the rate of change that we have right now is not the same as we've seen in the Eocene. I think it partly comes down to addressing the unknown nature of what some of these impacts are going to be, and it partly comes back to the kind of work that Danny was presenting earlier, is the fact that we can get an idea from the geological record about what some of the impacts will be when we've had kind of geologically normal rates of change. But the question then has to be, and the danger becomes, what happens if you make those sorts of changes under time periods which are substantially contracted? And I think that's where a lot of the danger and a lot of the risk in terms of how we're going to be able to cope in the future actually comes from. And so we need to be precautionary, we need to be careful, we need to try to get the situation under control as quickly as we can.
A question from Gavin, with increasing computational power, will we see more modelling efforts focusing on transient signals in the geological record? And if so, how useful would these be versus the current focusing on equilibrium states?
Yeah, that's a really good question, Gavin. I think one thing we are already seeing is we are seeing more and more transient climate studies, which are coming out in the context of paleoclimate modelling. And the improvements in the computational power that we have is certainly enabling that work. I think one of the key things which remains a limitation into the future in that context, particularly when we start thinking about applying those sorts of transient climate modeling techniques to intervals of time further in the past, is being able to come up with really robust and sensible transient forcings for those particular models. So it isn't actually just the technology, if you like. There's going to be some work to do in figuring out what would be sensible in the context of initial forcings and transient forcings for a modeling framework like that for different intervals of time. And I think that's an interesting challenge, and it's certainly a challenge which is well worth taking up.
We are running slightly over, but I just want to ask one last question, which is a really nice question from Pallavi. We have a tendency to become slightly temperature obsessed, and Pallavi's asking, please can you say something about how paleoclimate records on hydroclimate can help us moving forwards?
Oh yeah, sure. So I think, you know, that this is absolutely critical, and the reality is there are more limited there are a limited array of tools and techniques that we have in terms of getting exact precipitation estimates into the past, but it's still possible, and we certainly need to be able to carry on that work. But I think one of the key things that we can also do is look at that in a little bit more holistically. So I think, you know, some of the older techniques in the context of actually working out the hydroclimate conditions into the past, some of the lithological indicators, some of the climate sensitive facies work that was done in this sort of space can really complement and enhance the number of data points that we have available, which can inform about hydroclimate variability into the past. So I think part and parcel is it's about trying to use all of the tools and techniques that we've got available to us, not necessarily just the ones that might give us an absolute estimate of precipitation change in the past, with also its associated uncertainties.
Thanks so much, Alan. I'm going to wrap up there and move on, but just a little reminder as well to all our speakers, please do jump onto the Q&A after your talk or at any point actually in the session, because there are additional questions that we're not able to get to. And don't forget as well, have a quick look in the answered questions, because there's lots of questions in there that are relevant to more than one speaker, and you might have something to contribute as well. So thanks very much, Alan. And I'm going to move on to our second flash talk of the afternoon, which is from Dr. Margot Cramwinckel. Margot is a research fellow within Ocean and Earth Science at the National Oceanographic Centre in Southampton. And her research is on Eocene warm climates to explore our Earth system states under higher CO2. She uses both proxies and model simulations to explore not only the climate, but the critical carbon cycling and that broader environmental response to past high CO2. And Margot is going to talk today about the early Eocene hothouse climate. So I'll hand over to you, Margot.
Thank you very much for the introduction. I have to say I've really been enjoying all of the talks so far. So thanks to all the presenters. All right. There is my presentation. All right. And thanks of course also for the opportunity to let me talk a little bit about my past year of pandemic postdocing in sunny Southampton. And I'm going to use these 5 minutes to show a little bit of my in-progress results on hydrological cycling in the warm Eocene. So that actually ties in pretty well to the last question we were just discussing. And the cat picture is just to help you stay awake and keep an eye out for some more. All right, I think that these two pictures clearly illustrate the importance of the water cycle, as mean annual precipitation on the left really shows the same patterns as population density. So greater density in areas with the most rainfall per year, as our food production, of course, depends on this. But moreover, the water cycle is also really important in linking the climate and carbon cycle together through runoff. So all in all, it's very important to be able to predict how hydrology will change in the future under future warming. And while we're pretty sure that the hydrological cycle will intensify as global temperatures rise, the specifics of this remain very unconstrained, as illustrated here. So these panels show future IPCC projections for scenarios of 1.5 and 2 degrees of warming under high emission scenarios. And in these panels, the cross-hatching represents areas where more than 2/3 of the used models agree on the sign of change. So the upper panels show good agreement. So all regions will basically warm under these scenarios, which makes sense. But in the lower panels, you can see that most model projections agree on more precipitation in the high latitudes and the equator, so those cross-hatched areas. But there are also large regions where the models do not even agree on the sign of change, so whether regions will get wetter or drier under future warming. So let's try and constrain this future response a bit by looking at the early Eocene, which can be used, as we just heard in Ellen's Haywood nice talk, as a partial analog to next century climate under high emission scenarios. Here are some scatter plots showing model values from a set of early Eocene model simulations as generated within the DeepMIP project, the Deep Time Model Intercomparison project. All of these plots have temperature change compared to pre-industrial on the horizontal axis, and they all have precipitation change compared to the pre-industrial on the vertical axis. So what we clearly see here is that for these latitudinal bands, so the tropics, the mid-latitudes, and the high latitudes, all models simulate increasing precip with increasing global temperatures. But looking at the subtropical band, some models actually predict wetter conditions, whereas other models predict drier subtropics. So that's a bit of an uncertainty there. Now, based on the comparison to the available paleobotanical proxies that are actually able to give you absolute estimates of precipitation for past climate, unfortunately, we really cannot say anything very meaningful about this difference, as there's very limited data availability in the tropics and subtropics. Also, the error bars are fairly large here. Now, an alternative approach to reconstruct past hydrology is to look at the isotopic composition of precipitation in terms of hydrogen and oxygen isotopes of water. And globally, the most clear pattern in this is this latitudinal gradient. Two major factors play a role here, and those are temperature and water vapor transport. So we have more depleted values at high latitudes due to increased rainout of the heavy isotopes during transport, as well as greater fractionation at cooler temperatures. And this isotopic signal of the rain can actually be recorded by plants in their leaf molecules, as plants take up water from the environment. And as these leaf waxes or long chain alkanes preserve very well in sediments, they have been widely employed as proxies for past hydrology. And they've also come by a couple of times in the talks we heard yesterday. So I've been extracting and measuring lots of leaf waxes from early Eocene sites from different parts of the globe, as well as compiling all the data I could find in the literature. And here I've plotted these results. I've plotted them together with the modern gradient. A note here is that I've just assumed a constant fractionation factor between my measured leaf waxes and precipitation, which is likely not realistic, but still, for now, it allows us to at least compare the shape of the gradient to the modern gradient. And in terms of this shape, there's some preliminary observations. So first, we have quite some new data from North America, and based on this data, those data nicely line up, and also pretty similarly to the modern gradient. Second, values in the tropics seem fairly depleted, which might be due to extensive rainout, which is known as the amount effect. On the other hand, values in the high latitudes seem relatively enriched, which has been related in earlier work to warmer temperatures and increased moisture delivery to the Arctic. And these observations seem to work together towards a strongly reduced gradient in isotopes, in precipitation isotopes in the early Eocene, although keeping in mind that the data is still fairly sparse in the lower and the higher latitudes, which is why I'm going to try and generate some more data there. And these are the yellow stars on this map. So, seeing as I've managed to talk myself past the 5-minute mark already, I would just like to thank a lot of collaborators, because of course this incorporates a lot of proxy data and model simulation, so a lot of people worked on that. And I'll just leave these next steps open for your thoughts. And thank you.
Thanks so much, Margot. Really nice to hear some isotope plant work. So we've got a question actually from the panel, because I'm just keeping an eye and checking I'm not overlooking any questions that are open. No. So Margot, the question for you: do we need to take into account the evolution of plants when interpreting leaf waxes as a proxy?
Yeah, good question. I think it's probably important that we keep in mind the large plant groups that these molecules likely derive from. so that's why I was also mentioning my constant fractionation factor that I'm using. So we might be able to use the plant assemblages to correct for the effect of different plant groups contributing to the analkane signal. And so, yeah.
This isn't meant to be an unfair question at all, but can I ask you, so I know there's so much more to say about the fractionation assumptions, and I wanted to just give you an opportunity to say that. So what assumptions might we think are problematic in assuming constant fractionation like that, particularly with hydrogen, because it's such a tricky one?
Yeah, so am I still sharing this slide?
Yeah,
okay. Yeah, so there's, of course, those plants are not taking up the precipitation directly from the air. They are actually taking up water from the soil. So that's one of the factors. Yeah, and you can target that by potentially looking at soil isotopes derived from models. Or there's also been some work on this forward modeling, which I'm going to look into if that might be a possibility to apply this. Yeah, other things to take into account are maturity of biomarkers and the actual source of the analkane. So what kind of plants they are deriving from? Are they actually deriving from higher plants? Yeah, but those are all things that we are trying to take into account as much as possible, and we'll be also taking into account more in the future steps of the project.
Thanks so much, Margot. Really lovely talk, and thanks for waking us all up with the cats.
Always good, right?
Thanks. So I'm delighted to move on to our last speaker of this session, and to welcome Jess Tierney to talk about the first question in the statement. So Jess is an associate professor at the University of Arizona, and her research focuses on the study of past climates over a variety of timescales, particularly using organic geochemical techniques and statistical climate reconstruction. Jess's postgrad and postdoc work was looking at defining East African climate over the last 60,000 years, and also established her as a world authority on biomarkers in paleoclimatology, and it's how a lot of us know Jess's work. Jess is a Packard Foundation Fellow and a Fellow of the American Geophysical Union, and is also an AGU medal winner in 2014. And she's also another of our lead authors on AR6. So Jess has been invited to discuss, we'll come full circle to the very first question in the climate statement, which is, what does the geological record of climate change look like? So I'm going to hand over to you, Jess.
Yeah, hi, Mary. Thank you so much for that kind introduction. And thank you to everybody, for tuning in today, this afternoon, this morning. Just a quick tech issue. So I am not sharing my screen. I'm just going to be in front of my slides like that. So if you want for me to be kind of front and center, go ahead and click on the three dots in the upper right-hand corner of my talking screen and click pin, and then I won't flip in and out if someone else makes a noise. So just a little tech hit there. So the question that I was asked to address today is, what does the geological record of Earth's climate look like? And what you see behind me is sort of an informed reconstruction, I would say, and sometimes it's a best guess, sometimes it's more quantitative than that, of global surface temperature for the past 500 million years. And this is actually a curve that's on display in the Smithsonian Museum in Washington, D.C. and here in the United States. And incidentally, we're working very hard to improve this curve. But what it does show, just broadly speaking, is that Earth's climate has experienced some dramatic changes in the past. There's a lot of drama going on. There are times when the Earth has been extraordinarily cold. For example, during snowball Earth, which we'll talk about in a second, estimates place its temperatures at, maybe as low as -50 C global temperature. So super cold. And then there are times that are super warm. And we've already heard about a couple of those times already this morning. And just now with Margot's talk about the early Eocene as being one of those greenhouse climates where there are no large ice sheets, the planet is quite warm. So I don't have time in 20 minutes to actually talk about all of these swings in temperature and so on. But so I'll just feature some extremes, right? We'll talk about extreme cold and extreme warm. And the bottom line is that we can learn a ton about how the Earth's climate system responds to external forcings by studying these extreme swings in climate in the past. And they are directly relevant for our understanding of future climate change as well. So let's go way back, probably farthest back that we've been in this session so far, to the snowball Earth time, 700 million years ago, when the Earth may have been completely covered in ice, land ice over all the continents, sea ice over most of the oceans, and maybe a few openings here and there. So this is a pretty extreme climate change. And first of all, you're probably wondering, how do we even know that this actually happened? Well, we have some incredible geological evidence of snowball Earth conditions that is found all over the world. And so when you're looking in the rock record for evidence of large ice sheets on land, you're looking for things like, right up here, glacial tillite, poorly sorted facies, striations left on the rock as large ice sheets are grinding away and messing up the rocks on land. In the ocean sediments, you look for things like glacial drop stones on the far left here, boulders that are rafted out by icebergs and then plop down and into the fine ocean sediments. You can see there a nice drop stone set in what is a banded iron formation. A drop stone dropped into a low oxygen ocean. And so, in fact, geologists have found these glacial rocks all over the world, all dating back to the time of snowball Earth, around 700 million years ago or so. And they find in high and low latitude rocks. But if we consider that the continents, of course, 700 million years ago were in a completely different place, it turns out that the evidence for glaciation is actually coming all the way down from the tropics. So we are seeing glacial tillites, we're seeing drop stones at the equator, which is extraordinary, right? So here is a distribution plot of the glacial deposits during the Sturtian, which is one of the snowball Earth times. And you can see that it's bounded between 60 south and 60 north because, in fact, there were no polar continents at the time. This is what the world roughly looked like. But we find glacial deposits all the way to the equator, right? So hence the snowball Earth idea. How do you get large ice sheets that are grinding away at rocks all the way down into the warm tropics? And so you can imagine that we're really pushing the Earth system hard across some important thresholds. And one of the reasons I like to talk about snowball Earth is that it is actually a type case for tipping points in the Earth system and non-linear behavior, if you will. So both getting into the snowball Earth and out of the snowball Earth involve pushing the Earth from one stable state into another across a sort of threshold where it can't really exist in between. So when we talk about getting into the snowball Earth, right, we have to cool the climate down sufficiently to grow ice sheets on the continents, which are largely equatorial, but also to extend sea ice from the poles down and closer to the equator. And what we can do is we can actually simulate this process in a climate model. And what we see is that once the ice passes about 30 north and 30 south, the system rapidly cools down to about -50 C global temperature and snowballs, completely glaciates over. So there's a threshold behavior. And why is that? It's because once the ice becomes extensive enough, the ice albedo feedback, a positive feedback in the Earth system, takes over. There's so much bright white ice on planet Earth, it's reflecting sunlight back to space. And so as you have more and more ice, the albedo of the planet increases to a dramatic level. And then ultimately you pass that threshold and go into the snowball state, extremely cold state. Again, we don't know exact temperatures here, but -50 C has been thrown out there as the temperature of a snowball Earth. Now, going out of the snowball, same issue, right? Now we have to warm the planet sufficiently to kick it out of this state. This is a stable state, the iced over state. You need to warm the planet sufficiently to start to melt the ice. Once you melt the ice past a certain threshold, though, then you have the ice albedo feedback in reverse. So the ice melts, you have less bright white surfaces reflecting sunlight into space, and you have a positive feedback, right? So how do you kick yourself out of the snowball Earth? How do you escape? Well, the answer is, you bet, greenhouse gases, a ton of CO2. So our best estimate is that we must have needed like percent level of CO2 in the Earth's atmosphere to kick it out of the snowball. Where is it coming from? Volcanoes. So even though the planet is iced over, tectonics are still active. And so you do have a buildup of volcanic CO2 over time. And slowly, that's going to build up in the atmosphere. There really isn't a sink for it because everything's covered up with ice. Eventually, the climate is warm enough to bust out of the snowball state. And you might have noticed there's actually an overshoot situation here where the Earth's temperature pops up to an extreme warm climate because of the intense amount of CO2 that's in the Earth's atmosphere. And so it follows from this theory that the post-snowball conditions must have been extremely warm. And so you actually have this crazy movement of the Earth's climate between ice state, sauna state, ice state, sauna state, back and forth through these snowball Earth events, because in order to get out, you have to put an enormous amount of CO2 in the atmosphere, and then the climate becomes very, very hot. Is there rock evidence for these hot conditions? The answer is yes. We have these spectacular cap carbonate deposits that are sitting right on top of the snowball Earth debris. Cap carbonates, these bright white limestones. And this is a telltale signature that the climate was warm, because once we really warm up the climate and amp up the hydrological cycle, we start to dump a ton of alkalinity from land into the ocean, and it builds up in calcium carbonate. So this is like telltale signature that this theory is working, that we must be going from a very cold state to a very warm state, and the culprit is CO2. All right, so what have we learned from snowball Earth? We can learn something about the importance of the ice albedo feedback, which is something that is happening today as we are ultimately melting ice sheets, right? And the importance of that nonlinearity, and the importance of CO2, obviously, in warming the climate. Now, when we move forward into the Phanerozoic, we have more quantitative estimates of what temperature change was like, and also what CO2 change was like. So what you're looking at here is a reconstruction of atmospheric CO2 going back 450 million years. And I don't have time to talk about how scientists do this, but it's an amazing process. We have lots of really cool tricks using paleobotanical indicators, using isotope systems to actually get at CO2. And so we now have a picture, a rough picture still with a lot of error bars, of how CO2 has changed. And what do we see writ large? So on top, I'm showing the times in blue when there's extensive ice sheets on land. So going back all the way to the left, we have the Ordovician glaciation and the Carboniferous glaciation, and then the late Pleistocene glaciations. And what you can see is every time that there's a lot of ice on planet Earth, CO2 is low. And then when there's no evidence for land ice, CO2 is high. So very simply put, CO2 is in the driver's seat. It's ultimately pushing the Earth system between icehouse climates and greenhouse climates. So now let's focus in a little bit on a shorter time scale, the last 100 million years. And actually, Margot just showed this picture in talking about the Eocene. But I'll just go over what you're looking at here. So we're looking at a reconstruction of global mean temperature, then that colored line on top, and then CO2 curve, same one that I just showed you, but now we're zoomed in on the last 100 million years. And so what we can see is over this time scale, the Earth's climate has been slowly cooling from an extreme hothouse climate in the mid-Cretaceous down into an icehouse climate of the Pleistocene. Global mean temperatures possibly peaking above 30 degrees Celsius in the mid-Cretaceous. Compare that to present day global mean temperatures of about 14 C, right? So that's a different climate. And CO2, generally mirroring temperature, although not perfect, but we can see that CO2 has been declining. And then we see, but for a long time before the recent icehouse, CO2 was much higher levels. So I want to talk about warm climates now, and I am going to focus on the early Eocene, which Margot already introduced to us, this time period around 50 million years ago, when CO2 was around about 1,000 ppm, maybe higher. There was no polar ice, and the climate was super steamy. And we have lots of indicators for how warm the climate was, but we can start with the most basic of ones, like the fact that crocodiles were living and thriving in the Arctic. So we find crocodile fossils in the high Arctic dating back to the Eocene. And that's like a first order piece of evidence that it must have been really hot, because these guys are cold-blooded, right? So they don't really do so well below about 20 degrees Celsius. So the fact that they're hanging out in the Arctic and doing okay, it kind of gives us a minimum bound on land temperatures there, that they must have been at least about 20 C on a mean annual level. We also see evidence of palm trees and baobab trees, so subtropical trees growing and thriving on the coast of Antarctica. These are some on the far left, some phytoliths that are preserved from these trees, and we find them right off the Antarctic coast. So again, a really good sign that the high latitudes were a lot warmer than today. And this sort of floral and faunal evidence actually fits really well with some geochemical evidence that we have concerning what the temperatures of the ocean were like. And so the blue line is our best estimate of Eocene ocean temperatures compared to today's ocean temperatures in orange. And what you can see is, in agreement with the crocodiles and so on, the high latitudes are around 20 Celsius. And then the tropics are warmer as well, sort of around 35 degrees Celsius or so. But you can see that there's enhanced warming at the higher latitudes. And that is a feature of warm climates. And we call that feature polar amplification. Polar amplification, more warming occurring at the high latitudes. And this is a very typical response to elevated CO2. And so here what I'm showing you is a model simulation of the Eocene. This is the change in temperature relative to the pre-industrial, and then comparing in the corner to the prediction from the last IPCC report for what temperatures look like under a high emission scenario, the RCP85 scenario. And what you can see is, even though the continents have moved around, the basic pattern is the same. The high latitudes warm more than the low latitudes. The land warms more than the ocean. And Paul Valdez touched on this yesterday, that basically, while paleogeography is important for regional climatology, moving the continents around doesn't really change global metrics, like the global latitudinal pattern of polar amplification or global mean temperature changes. And for that reason, we can use the past, we can use paleoclimates to really learn about these physical processes. The physics of the climate system stay the same. And so you can see the remarkable similarity between these patterns, which indicates, what's the shared forcing here? It's CO2. So, why is polar amplification happening? So first order, right, if you get rid of the ice sheets at high latitudes, right, you warm them up by a lot, because those ice sheets, again, ice albedo feedback, are reflecting sunlight back to space. So once you take them away, more energy is absorbed. And this is one of the reasons why we see polar amplification. But another reason that we're increasingly appreciating actually has to do with clouds. And so in the last few years, there's been a lot of research looking into the role of clouds, and particularly the low stratus clouds, the stratus decks that hang out in the subtropics and in the polar latitudes, and the role that they might play on the energy balance of planet Earth. So these particular kinds of clouds, stratus clouds, they reflect sunlight. They're bright and white, and they're low. So sunlight comes in, it bounces off and goes back to space. So their general role in the climate system is to cool the planet down. But at high CO2, what happens is these stratus decks start to disintegrate. They break up, they essentially rain out, rain away, and more sunlight can then come through, which means that this is a positive feedback. At high CO2, you break the clouds up, and then you allow more sunlight through, and you warm even more. And we're now learning that this is a key element of explaining polar amplification in warm climates like the Eocene, as well as in our future. All right, so now I want to focus in on what we call aberrations, or rapid climate change events that represent this sort of extreme but temporary excursion of the climate system. And I want to talk about the Paleocene-Eocene thermal maximum. So Daniela this morning already introduced some of the effects that the PETM had on ocean ecosystems as it was a major acidification event. So the PETM and its sort of sister hyperthermals, as we call them, and that's sort of self-explanatory, are happening right before the peak warmth in the early Eocene climatic optimum. And so about 55.8 million years ago, we have the PETM event. And just as a review of what's happening during this event, basically, first of all, CO2's bumps up temporarily. We think this is due to volcanism in the North Atlantic. And then at the same time, we see a bump up in global temperature. And we also see a decline in ocean chalk or calcium carbonate, which Daniela talked about this morning. And in fact, you can, as she pointed out, you can see the PETM straight up in the sediment cores that are collected to capture the event. You can literally see it in the color of the mud, which is spectacular. So before the event, on the far left here, we have sediments that are rich in calcium carbonate, everything's fine. And then boom, we hit the event, there's a sharp boundary, the PETM is starting, and the ocean acidifies. And so all that bright white carbonate that's in this sediment core has been dissolved away because the pH has dropped. And then we see that this red clay kind of take over, that's what's left. And the red clay hangs out for a while. 10,000s of years later, we're still not recovered. So it does take a while for the Earth system to buffer carbon dioxide. And that was a topic that came up earlier today. It's really on geological timescales, right? Now, finally, you see the return to the chalky sediments 100,000 years later. So the total recovery time, which we can directly learn about from the PETM, right, is on that order of time, 100,000 years. And that's when all of the Earth's mechanisms for buffering CO2 come into play and can return the system back to normal. So from these, beautiful sediment cores and study the PETM, we can learn a lot about how the Earth system processes a sudden increase in carbon dioxide, which is obviously relevant for where we're headed. I just want to put the context of the PETM directly next to some of the future predictions for surface ocean pH. So this is a sort of a new prediction of possible trajectories of ocean pH by 2100, with the colors corresponding to the amount of CO2 we emit. So the blue would be the lowest emissions scenario, and the red is the highest emissions scenario. And we estimate that the drop in pH during the PETM was about 0.3 pH units. Now, it doesn't seem like very much, but remember that pH is a logarithmic scale, and that is a ton more acidity in the ocean. And organisms are definitely not adapted to deal with that big of a change in acidity. And so we can see, which is shocking to me, that if we continue on a high emissions scenario, we will actually meet, if not exceed, the PETM level acidification before 2100. So this is something that your children will see in their lifetime. We could see the complete destruction of our coral reefs, of calcifiers in the ocean on a human timescale. So pretty scary. So we don't want to do that, right? All right. So one thing I'm really interested in is, what did PETM climate look like? What I'd love to do is get in a time machine and go back and be like, whoa, what's going on, right? But of course we can't do that. So we have to reconstruct what the PETM looked like from geological information and from climate model simulations. So what you're looking at here on the left is a blend. So Dr. Otto Bleisner yesterday mentioned that we're now using this technique where we're actually blending proxy climate information with climate model simulations to produce a hybrid product. So we can get a full field picture of what the PETM looked like. So the panel on the top shows you the blended estimate of the change in surface air temperature between the PETM and right before the event, what we call the pre-PETM. So what you can see from that plot is polar amplification, right? So we see a much bigger change in temperature in the high latitudes, up to 9 or 10 degrees C or so, than the low latitudes. The global increase in temperature is somewhere around 5 degrees Celsius. This actually agrees pretty well with previous work. But something that's a little bit scary to me is that our best estimate right now is coming out as an average global temperature of about 35 C in the absolute, which is really, really freaking hot. So we'll see if that pans out. This is work in progress. I just wanted to show you something hot off the presses. But that is super toasty. So that's a bit of a surprise, and it's a little hotter than previous estimates have put it at. Now, we talked a little bit about the hydrological cycle. I'm glad that it has come up because water is so important in thinking about climate change. And so with this technique, we can also get a blended estimate of the change in precipitation in the PETM. And what you can see is that there's a lot of that sort of blue-green color. Basically, most places are getting wetter, which makes sense because we're warming the climate. and overall warm air holds more water, and overall you expect things to get wetter. But in particular, the tropics are much wetter and the high latitudes are much wetter, and there's a little bit of drying in the off-equatorial regions. And that actually fits again with what we think happens under high CO2 worlds. And it also looks a lot like some of our future projections of precipitation change. So this point was made earlier by Alan and Diana and Daniela, which is that although the PETM was extreme, it's important to remember that it was still not as fast as what we're doing right now. So the blue line represents the rate of warming during the PETM, and the red line represents the rate of warming that we're doing right now. So the current rate of emissions, of CO2 emissions, of warming, is an order of magnitude faster than the PETM, which is pretty extraordinary. So it is a really extreme thing we're doing to the climate system right now. We can call it the anthropogenic aberration. And as sort of a fun thought experiment, one thing we wanted to do was visualize what the anthropogenic aberration looks like on the geological timescale, right? So if you were to zoom out and you were a geologist a million years in the future, and we're looking back on the anthropogenic aberration, what would it look like? So to give some context to that, what we did in this plot is we actually ran out the emissions trajectories, low, medium, and high, to 400,000 years plus, to see what happens to CO2 as the Earth system starts to process it. You know, ultimately the Earth system will recover, right? There's these natural processes that buffer CO2. The problem is, if you look at the x-axis, the time scale, right? So the time scale is relative to 2020, and you can see that our species evolves around 300,000 years ago. And we have spent our entire existence on planet Earth between CO2 levels of 180 and 300 ppm. That's it. We're an ice age species. We know nothing about these warm climates. We've never even felt it. And so all of a sudden now you see industrial revolution, 2020, 2021 now, we're already outside of the envelope of CO2 levels that we've seen in the last 300,000 years. And then of course we have these three very different trajectories. Low emissions, you know, we pop up, but then we get things under control. Middle emissions, we pop up to levels that are above the Pliocene 3 million years ago. And you can see that there's sort of a long tail of recovery. And then the high emission scenario is pretty terrifying, right? That would put us at CO2 levels that possibly exceed things that we've seen in the hothouse climates or comparable to them, like the early Eocene or mid-Cretaceous. And it takes tens of thousands of years to even come down on that steep slope, and then all the way out to multiple hundred thousands of years to completely go back to normal. So on the Earth system timescale, this looks like a blip, but for us and the other species that we share this world with, it is actually a state change. All right, so with that, I will end, and I'd be happy to take some questions if there's time.
Thanks so much, Jess. Yeah, definitely gonna keep us here for a couple of questions if that's okay. I'm gonna start with a couple of more general questions, Jess, that are sort of bringing together a few different points, both from the panel and from the chat. I don't know if I could ask you to go back to your lovely kind of Phanerozoic summary plot that you showed a few times with the kind of evolution, temperature evolution through the Phanerozoic. Don't worry if not.
The one at the beginning, or
yeah, the one right at the beginning, and then that you showed again at the start.
Go back. There we go.
I just wanted to give you a chance to talk a little bit about what are the greatest sources of uncertainty in this, which axes hold the uncertainty, and where does that uncertainty come from?
Yeah, sure. So there certainly is age uncertainty in our understanding of this, but it's going to be the x-axis uncertainty on these timescales is going to be smaller than the y-axis uncertainty. And yeah, so we don't have thermometers, right? So we can't just like go back and know what the temperature was. We have to rely on our entire arsenal of both geochemical indicators for temperature and also, floral indicators for temperature, or crocodile indicators for temperature. And so to create a curve like this, you really need to bring together like all the information that you possibly can, compile it. And then, of course, the proxies, we call them proxies because they're standing in for temperature. They're not necessarily, they're sensing temperature, but they're usually recorded in a unit that's not temperature. And so you need to translate that into temperature units. which requires some statistical modeling. And so it's actually non-trivial, right? So while I think the general trajectory of this curve is going to stay the same, because we know some very basic things, like we know that, during the Carboniferous, there were really large ice sheets, so it's probably cold. The details will evolve as we get more and more geological information that will get us closer to estimating temperature. So it'll be exciting to see how this curve evolves and how it improves in the next few years.
Thanks so much. There's a question from Matthew in the chat, who's asking, in a hopeful way, if we're looking at the PETM as an analog for RCP 8.5, if we, with our hopeful view on think about perhaps undercurrent climate pledges, that being a more distant prospect, where would we look for analogues for RCP 7 or 6 instead?
Well, it depends on what your baseline is for analogues, because if we're talking about pH change, I'll just go back to that. So high emissions here is SSP 7. And so, in fact, the PETM is still an analog for SSP 7 in pH terms. So I would say that, just a basic analog. I mean, as Alan discussed, the term analog is sort of loaded, and you can sort of take that to be very literal or not. But I actually think that PETM is pretty relevant for understanding even middle to somewhat high trajectories, because we are getting very close to the level of acidification that we've seen on this level. So yeah, still an analog, I would say, for those middle emissions. Now, the lower emission scenarios, middle road, as Alan discussed, maybe the climates that are not so extreme, like the Pliocene or the Miocene warm periods, are better those are better equilibrium analogs. But of course, the PETM, like what we're doing today, is transient. And that's sort of the power of studying it, because it does represent like a transient thing where the system is not in equilibrium, which is actually what we need to understand, right? Because we're not going to see equilibrium in human timescales.
Right. Thanks for that, Jess. I'm going to try and summarize a few. There's lots of questions in the chat around what else, orbital forcing and these sorts of things, and questions around, clearly there isn't a perfect, simple relationship between CO2 and temperature, obviously, because it's the planet, and why would there be? So the plot that you showed during the Oligocene, and I guess I would say, could you talk a little bit about whether that's around uncertainties in the records or an actual decoupling at time periods of the CO2 temperature relationship?
Yeah, absolutely. I really think that those times when, I'll go back to the plot, that CO2 and temperature don't follow one for one. I would bet money that they're going to match, that mostly this reflects uncertainties in our ability to estimate CO2. So I'll give you some examples. So for one thing, you can see that timing of that Eocene Oligocene transition is a little bit off. And that is actually coming from a couple proxies that seem to be sort of shifted in time in the CO2 compilation. But if you actually look, for example, at specifically the boron data, they actually, match the mean temperature record pretty much precisely. So I think as we get more data over that transition, they're going to start to come in alignment. Another example is between 60 and 70 million years ago, the CO2 estimates seem a little bit low. And the problem is we have a real drop off of data in the late Cretaceous and the Paleocene. And so there's a lot of data in the Eocene, and then the Paleocene's a little more boring. So maybe we don't measure it as much, but I am absolutely confident that once we extend the data into this curve is going to reshape, because, ultimately on these timescales, CO2 is in the driver's seat. So orbital stuff, that's important on smaller timescales, and it changes, as we heard the other day, the seasonal balance of energy, right? And so it's really important for things like regional climates, for monsoon systems, but on these long geological timescales, it's basically what's controlling the climate. Solar luminosity, as Paul Valdez said, right? The sun is changing its output very, very slowly, and then paleogeography, less important, right? And then it's CO2. It's greenhouse gas. It's CO2, right? So that's it. So I'm pretty sure that this mostly reflects uncertainties in our ability to reconstruct CO2. It's not easy, as many people in the audience really appreciate.
That's a really lovely point to summarize. Paleoclimate, it's just not easy.
Yeah.
Thank you so much, Jess. I'm going to say a huge thank you from me to everybody who's been speaking today, to all of our speakers, and to everybody who's participated in the Q&A as well. Thank you so much. A reminder again to our speakers that there probably are a few questions left in there, and do feel free to engage with those. I'm sure everybody's desperate to grab a cup of tea, run up and down the stairs a couple of times. So we are taking what is now, sorry to say, a 50-minute break. We're back here at 4:45 for invited talks from Rachael and Cal, and then our poster session. So huge thanks from me, and we will see you all soon.
Okay, everybody, let's get started for the last session. So my name is Charlie Williams. I'm a research fellow in climate science at the University of Bristol, and I'm delighted to be your chair for the last session. So we have two final speakers, Cal and Rachael. And in between these, we're going to have the flash talks, where for those of you who submitted a poster, you had the opportunity to pre-record a 1-minute presentation on your work. After that, at the end of the session, we're going to go into breakout rooms where those of you with posters will have the opportunity to present your poster, and people can ask questions. So before that, I'd like to introduce our first invited speaker, Kaustaubh Thirumalai. Cal is an assistant professor at the University of Arizona in the US. His interests are wide. They include climate variability, paleoclimatology, and paleoceanography, as well as extreme events and how the geological record can inform us about future projections. Today, he'll be talking about question 4 of the statement. What does the record indicate about global versus regional change? So over to you, Cal. I will turn my camera back on at your 2-minute warning. Over to you.
Okay, thank you very much, Charlie, and thanks to all the organizers for giving me an opportunity to share some of my research here. And the topic that was assigned to me, the question is, what does the geological record indicate about global versus regional change? And naturally, as others have talked about, it's tough to cover all the different topics of regional change throughout the entire history of the Earth's geological record. So I'm going to apologize straight up and basically focus on a couple of aspects that I'm working on. And so let me start off by showing you a graph that many of you have already seen and many speakers have already talked about in this workshop. And in particular, so this is a graph that's spliced together by Burke and others in PNAS. And you can kind of see this is sort of the evolution of global climate temperature over time, over geological time, from 60 million years ago all the way into the future, with future projections as well. And what I wanted to kind of indicate here is that we're really getting an increasingly detailed picture about past and future evolution of global climatic states. And it was fortunate that I'm following Jess Tierney, because Jess really nicely gave an overview about how, particularly in the Cenozoic, the major control knob on global climate, as well as global temperature evolution, is really carbon dioxide. So CO2 is a major control knob on global climate, including moving from a greenhouse world into an icehouse world. And we have to be really cognizant about which world we want to move into in the future. Undoubtedly, it's getting warmer, but depending on the different trajectories of CO2 emissions, we're going to end up in different worlds. And so the trajectories that really we have in line for the future they're going to hold really strong implications for global climatic evolution, but also in particular future regional climate variability and extremes. So when we take a look at these sort of disparate states that the future might hold for us, the way that these states trickle down into sort of regional hydroclimate evolution and regional extremes is still uncertain. Now, we know for a fact that CO2 is increasing, and that's going to induce warming across the planet. And so some researchers, there's been a lot of work on trying to figure out how warming is actually going to impose changes in extreme hydroclimates, so extreme precipitation. So here's a figure from Fall and others in Nature Climate Change from a couple of years ago, where they sort of disentangled the impact of the thermodynamic contribution and the dynamic contribution of changes in future extreme precipitation. So on the left-hand side, what you can see here is basically an entire globe that's kind of about 3 to 9%, maybe a little bit more in certain areas. And what this is talking about is the fact that the thermodynamic contribution, the fact that we're going to increase CO2 in the atmosphere, is going to essentially supercharge the hydrological cycle and allows the atmosphere to hold more water vapor. And the graph, the scale right here is the percentage change in the hydroclimate extremes per degree of warming. So when you disentangle the thermodynamic contribution, we know that the increased warming is certainly going to impose a larger change in the hydrological cycle that leads to larger extremes. Now, I also would like to point out that this is a multi-model ensemble composed of over 20 models. And these dots that you see here indicate that over 80% of the models agree on the sign of change. So all of the models across the globe are in agreement that the thermodynamic contribution is going to increase the number of hydroclimatic extremes and regional extremes all across the planet. Now, that said, though, we're not only going to get thermodynamic changes, even though the world is warming, we're going to have a lot of changes in the dynamics as well. So on the right-hand side here is a plot that shows the dynamic contribution to these changes in hydroclimate. And as you can see, there's a lot more nuance here and large changes that go from more negative changes to positive changes as well. And really critically, many of the models are not in agreement even on the sign of change in the in future extremes. And so in particular, these authors actually also looked at the uncertainty of changes in the full scaling. So this plot right here at the bottom shows you the uncertainty, that is the sort of the spread between the models that contribute to this dynamic contribution. And you can see here that these changes are large. The uncertainty is large, on the order of 25% per Kelvin, where the signal in itself is on the order of 30% per Kelvin. And so the bottom line is that the future hydroclimate extreme evolution is really uncertain, largely owing to how climate dynamics are going to change as we move into a warmer world. Regardless of how warmer that world might be, you're basically going to have extremely substantial implications for regional climate evolution. And one thing that I'd like to point your eyes towards is looking at where we have the largest uncertainty. And that uncertainty arises in the tropics. So you can see that tropical uncertainty in hydroclimate extremes is exceptionally large. And this is kind of one of the major motivations for my own research, is that the tropics are where we have the largest number of people. So tropical climatic impacts are going to disrupt a majority of global population. In particular, this is a kind of some of you may have seen this before, but it's kind of a staggering statistic, is that more people live inside that circle than outside of it. And moreover, we know that climatic extremes, including things like drought, wildfires, and extreme flooding events, are increasing in these countries that are particularly vulnerable and hold a majority of the Earth's population. And so here are just some examples of pictures showing you some of the extremes that are happening. So here's a picture of drought in Myanmar in 2016. This is extreme winter monsoon flooding in Chennai in 2017. And then there were widespread wildfires across Sumatra and Java in Indonesia in 2017 as well. And so in particular, the sort of the socioeconomic currency of regional climate change is hydroclimate extremes. So we want to really be able to anticipate the different types of extremes that are important for different regions and how that's going to evolve as we move into the future. And the bottom line is that the sort of the transferal of global change into regional climate evolution, variability, and extremes is still unclear. So what does this look like? What does future climate variability in the tropical oceans look like? And largely, mind you, many of these events have been attributed to changes in the sea surface temperature domain in the tropical oceans. So what does that look like when we look into the future? Well, so here is a plot of the multi-model ensemble mean of future changes, of projected changes in sea surface temperature variability during 2100, subtracted from the present day simulations. And so this is the mean change in variability across 39 different models, and going from a scale of minus 30% to plus 30% relative to today's variability. And the bottom line here is that a large part of this graph is white at 0%. Now, does that mean that models suggest that there's going to be no change in variability? That's not true. What this actually says is that there's a lot of models, some suggesting increases, some suggesting decreases, such that the average ends up being zero, close to zero. So they disagree on what's going to happen to the future of climate variability in the tropics. And largely this arises from uncertainty in the evolution of the El Niño Southern Oscillation. But another thing that emerges out of this picture is that models seem to converge, at least some of them do, in order to sort of overcome the noise amongst them, that there's a stark increase projected in Indian Ocean SST variability. And as I showed you before, the Indian Ocean and the Indian Ocean rim harbors countries that are really critically dependent on sort of steady rainfall as a direct impact on their socioeconomic stability. And so we really want to try and understand what's going on in the Indian Ocean and whether such incredibly large changes of 30% in sea surface temperature variability are even plausible or not. So zooming into the Indian Ocean realm, here is the sort of the projected future Indian oceanography. So what I'm showing you here are the projected changes at 2100 relative to today in anomaly space. So all models agree that the Indian Ocean is going to warm. There's no question about that. But very interestingly, the models are suggesting that the Eastern Indian Ocean is actually going to warm a little bit less than the Western Indian Ocean. And in particular, you can see that the Arabian Sea here, it warms a lot. That's already happening. Many people have focused their research on this aspect. But again, this is the future projection, that there's less warming in the East, stronger warming in the West. And this asymmetry in the zonal gradient basically triggers anomalous easterly trade winds that do not exist today in the permanent mean state of the Indian Ocean. And so if I could direct your sort of focus on the equatorial Indian Ocean, you can see here that there's this stark contrast in the zonal SST gradient, where the West warms more than the East. And basically you have the onset of these anomalous easterlies. And essentially the models are suggesting that this altered mean state is going to elicit higher air-sea coupling or stronger ocean atmospheric interactions that are going to give rise to larger climate variability. So the anomalous zonal temperature gradient in the future is a tenet that models are suggesting, and we want to try and understand what that can actually mean for climate variability and regional climate change across this densely populated region. So the sort of the thrust of my talk today is basically trying to establish that the geological record can absolutely furnish dynamical parallels across altered mean states to really try and assess the machinery of the climate system. So in other words, the question is, can we go back in time to try and look at whether the Indian Ocean ever had such a scenario that existed where the zonal SST gradient was much different and altered completely relative to today. And I'm not going to go into too much details into the background climate state, but as several of you have already witnessed with some of the speakers in the workshop before, I'm going to be focusing on the last glacial maximum that happened about 19 to 21,000 years ago. And we've identified this date as a potential dynamical parallel to the global warming scenario. And I'm going to explain how. But this plot right here is taken from my collaborator's paper in 2018. Each one of these circles right here basically represents a sea surface temperature proxy reconstruction. And the color inside it tells you the degree of cooling during the last glacial maximum. And so essentially what I'd like to point out right here in the equatorial Indian Ocean is that the proxies are indicating that the zonal equatorial temperature gradient in the glacial Indian Ocean was altered, and altered in a way such that the eastern Indian Ocean cooled a lot more than the western Indian Ocean. So this anomaly basically was imposed in the zonal contrast. Now, in combination with climate models, I'm going to show you a figure with a simulation from CESM 1.2. So now the colors are basically coming from the climate model because we can query what it says across space. And we can also look at what the climate model has to say about the changes in the wind stress regime as well. So the LGM simulations and the proxy data, they both indicate that the Eastern Indian Ocean was a lot cooler than the Western Indian Ocean. And the simulations tell us that there was this onset of these anomalous easterlies in the equatorial Indian Ocean 20,000 years ago. Okay, very intriguing. When you force a model with these LGM boundary conditions, they agree with these proxies, and they also suggest this onset of these anomalous easterlies that we're looking at in the future that we want to try and assess. Now, to kind of simplify this and to really draw out this dynamical parallel, let's assume that this is the modern gradient in the Indian Ocean. So this is the western, and it's the eastern. The LGM case is basically telling us that the east cooled a lot more than the west. And the global warming paradigm is such that the west is going to warm more than the east, but the zonal contrast is similar. So the question really is, how do we take advantage of this zonal contrast? Okay, so, and here is what the model actually simulates for the change in the SST standard deviation. So the variability of sea surface temperatures in the LGM according to the simulation. And the model suggests that there's a really, really large increase in the SST variability during this time period. So really, again, we want to take a look at how can we take advantage of this scenario. So here's just a schematic showing you the sort of the parallels in the global warming scenario and the last glacial maximum scenario. And I want to really be key here. I want to point out that we are not headed into a colder state in the future. There are different dynamical drivers for why these patterns arise. But the fact is, the similarity in these dynamics should be able to tell us something, and we ought to be able to learn whether such dynamics can actually operate in the Indian Ocean or not, in spite of the mean states, okay? So again, we're not going into a last glacial maximum. That's totally out of the question. There are different drivers for these patterns, but we want to learn from these dynamical parallels. And so the question really became, how can we reconstruct SST variability during the last glacial maximum? And I'm going to skip on a lot of the nuances and the details. I'm happy to answer them in the chat. But for this particular project, we looked into calcareous protists, known as foraminifera, that others have talked about in this workshop. But the analysis of short-lived individual foraminiferal shells, we use that as a technique to assess whether the Indian Ocean actually harbored larger climate variability in the past. So I'm going to cut to the chase here and show you some of these results. There's a lot going on here, so let me walk you through with from the left-hand side to the right-hand side. So we chose these 4 different sediment cores, and each one of these black dots right here represents an individual foraminiferal measurement. The orange represents modern sediments, and the basically the blue represents last glacial maximum sediments. And so the point here is that these are oxygen isotope measurements, and suffice to say that on the left-hand side is cooler, and on the right-hand side is warmer. I have, of course, removed the mean cooling between the 2 states. So I've put everything, aligned it on 0 just to look at the variability. So of course, the last glacial maximum was cooler, but we're trying to compare the variance between the modern state and the last glacial maximum. And essentially what emerged out of this analysis is that pretty much across these 3 different cores where the model actually simulates increased variability, we actually see that the data, these foraminifera, are indicating much larger variance, both in the cold state, in the cold tails, as well as in the warm tails, during the last glacial maximum. So you can see here how these variance increases right here. And in our southernmost site, we actually did not see a statistically significant change in variance. However, that is also what the model simulates as well. So right here is the translation of these individual foraminiferal results into the standard deviation, the magnitude of standard deviation between the change between the modern and the last glacial maximum. And the circles are telling you about what the actual data say. And the squares here are from those particular grid points in the actual model. So there's model data agreement here in both the pattern as well as the magnitude of enhanced climate variability in the glacial Indian Ocean. So both these completely disparate lines of evidence are telling us that the Indian Ocean is capable of harboring a lot larger climate variability than we see today. So the SST variability that actually gives rise to a lot of these hydroclimatic extremes was a lot larger in the last glacial maximum. And so this agreement between the model and the data actually gave us some confidence in investigating the model and to try to see what nuances the model's dynamics actually can tell us about. So this is a Hofmöller diagram. I'll walk you through what this exactly means. But on the left-hand side is the simulation for the glacial Indian Ocean. And on the right-hand side is observations from the modern Pacific Ocean. So essentially what this right-hand side tells you, this is a composite of all El Nino events and La Nina events that happen on record in terms of instrumental observations in the Pacific Ocean. And the way to read this is you start from the March of year 0 all the way up. So you're going forward in time as you move down in this plot to December of the next year. The colors are telling you about the intensity of sea surface temperature warming or cooling. The arrows are telling you about the direction of wind stress anomalies. And these contours are telling you about changes in the subsurface depth of the thermocline or the subsurface structure of the ocean. And so essentially what happens during an average El Nino event is that the central and the eastern Pacific basically warm, and this warming peaks during December. And this warming occurs with the onset of these anomalous westerlies in the Pacific Ocean and a deepening of the thermocline in the Eastern Pacific. Now, we see very, very similar dynamics that are occurring in the Indian Ocean according to the simulation as well. There are some differences that you can clearly see here, but I would like to highlight the similarities in terms of this sort of dipolar nature in the equator. So these are both averaged across 5 north to 5 south. So these are equatorial processes that we're looking at. And you see this onset of these anomalous westerlies that give rise to warming here that are accompanied by a halting of upwelling as well. Some of the key differences that this tends to peak during August, during the summer monsoon months, whereas the El Nino, of course, as we all know, peaks during the December, January, February time. Okay, so the simulations, when we dive deeper into them, they suggest that the Indian Ocean harbored this equatorial mode, or we're calling it the Indian Ocean El Nino colloquially, but this equatorial mode is unobserved today. We do not see this mode in the permanent mean state of the Indian Ocean over observations. But during the last glacial maximum, this mode seems to have existed, and the data, the foraminiferal data, seem to confirm that. Now, very interestingly, we have to ask the question about the future activation of this Indian Ocean El Nino, and model simulations from a paper from that we put out last year from my collaborator Pedro D'Inezio. And you can see the sort of the parallels between the last glacial maximum in terms of sea surface temperature variability and when it comes to greenhouse warming. So this is really unusual, that you have to think about it, that are we currently in an unusual state? So did the entirety of human civilization and the sort of the rapid flourishment of populations in this densely populated region, did that happen under sort of a precarious balance, such that today we're in neither extreme state, neither a cold state nor a warm state, and we don't have this sort of equatorial mode that exists in the Indian Ocean. But simulations in concert with paleoclimate data indicate that the Indian Ocean can harbor this larger variability. So both warmer and cooler states can potentially induce this equatorial mode. So are we at kind of the precipice where this mode can actually be triggered and be activated? So some of our research, we actually looked into what might happen if this mode was activated in the future. And I'm going to spare you the details, but the bottom line is that if this mode were to get activated, we're going to have a lot more uncertainty in anticipating hydroclimate changes across this region. So you can kind of see here that during the warm events of this mode and the cold events of this mode, there are characteristic hydroclimatic signatures here that are basically going to impose a lot of variability and that are going to contribute to extremities in these densely populated regions in the future. And so this is alongside the impact of El Nino, for example, on this region, as well as the Indian Ocean dipole on this region. And they're going to have substantial interactions with the Indian monsoon and the Asian monsoons that are going to further increase the uncertainty in future regional climate evolution in this particular region. So I'm going to stop right here and just quickly summarize what I've just presented on global versus regional change, admittedly just for one region. So I apologize for that, not necessarily showcasing some of the other regions, but given that this is where I focus on and where I think a lot of vulnerable populations are going to be dependent on sort of how well we anticipate the future trajectory of regional climate change. So the 4 key points that I'd like for you all to take home with you is that there are nonlinearities that exist between global climate and regional climate evolution. And so just because the world is going into a warmer state doesn't necessarily imply that there's going to be sort of concurrent increases or changes in the extremes across the board in many of these regions. And each region is going to have sort of its own sensitivity, both socioeconomically, but also dynamically with different types of extremes. And so these dynamical parallels in the past can provide really excellent perspective on future regional climate change. And there's much to be learned about the machinery of the climate system when we look back into both warm and cold global climate states, as Jess Tierney kind of showed with the extreme states in her previous talk. And so the bottom line for the future Indian Ocean is that there's a question of, is there much larger variability yet to come? So I'll stop right here and I'm happy to take any questions. So thank you very much for your time and for the opportunity to present here again. Thanks.
Okay, thank you very much, Carl. Really, really interesting talk. So we have a number of questions. Firstly, from one of the panelists, are there any proxies that can tell us about daily or weekly scale variability?
Excellent question. So the question is, are there proxies that can tell us about daily or weekly temperature change? One, let me just say that when you look at these time periods going further back in time, it's extremely difficult to get well-resolved proxies. But that said, new techniques, reinvestigating sort of well-developed proxy methodologies are really beginning to show us some really high-resolution daily and weekly reconstructions. Now, it's still, admittedly, there's a lot of uncertainty, but I can give you an example. In a study that I was involved with a couple of years ago, there are some really, really fast-growing gastropod shells, for example. So snails, and in particular, things like the giant African snail, for example, that grow really fast. And we've shown that they actually incorporate into their skeleton geochemical fingerprints of weekly to subseasonal rainfall variability. And we can find these shells, for example, across outcrops, and we can actually query them as to what they might tell us about, for example, active periods or great periods in the monsoon domain. Other ways that people can actually look into these super high resolution or ultra high resolution variabilities, you can really scan sediments, for example, that are accumulating at a very, very fast sedimentation rate and try to understand things about weekly to subseasonal climate variability. And then finally, I'll just make a pitch for ostracods. These are basically crustaceans that live in both lacustrine as well as marine environments, and they actually molt. And when they molt, they basically deposit their entire calcium carbonate shell in a matter of hours to days. And so they're going to lock in whatever the environment, those geochemical signatures of the environment at that particular time. So there are ways forward. It's fraught with uncertainty right now. But I think with more records and improved nuances in the technologies, we can really try and get a handle on what that might actually hold for us in terms of our understanding of future changes on those really ultra high resolution timescales.
Okay, thank you. So we have another question. Can you speculate on what the role of the Indian Ocean El Nino might have had during previous greenhouse climates?
Yeah, this is a really good question. Short answer is that we have a hunch, but we are yet to test this. So we can look into, for example, many of the warmer analogs that multiple people here in this workshop have described. For example, the marine isotope stage 5 or the Pliocene or the PETM. And we can try to think about, what the Indian Ocean as, with the modern geography, what that might hold for this onset of the Indian Ocean El Nino during these greenhouse periods. And so this is a work in progress, but we do have some simulations for the last interglacial as well as for the mid-Holocene that seem to suggest that perhaps a weaker but still a consistent form of this Indian Ocean El Nino existed during both of these time periods as well. We don't necessarily have the data yet. That's a work in progress, but that's an excellent question and something that we're trying to focus on, whether we can look into the geological past for greenhouse periods and try to see whether the Indian Ocean El Nino or this equatorial mode existed.
Okay, and then we have, I think, time for one more question from the audience. So the question is, how does the Indian Ocean El Nino interact with the Pacific ENSO? And are there any patterns for intensifying and stabilizing the impacts?
Again, that's a very excellent question because we know that today many of those extremes, including the ones that I showed you, are really triggered by changes in the Pacific El Nino. And so the Pacific El Nino has a strong hold on the Indian Ocean realm. And the short answer is that when you look at the last glacial maximum, according to some simulations and some data, it's a little more uncertain in the Pacific, we have evidence that the El Nino and the ENSO system was actually weaker during the last glacial maximum. And because it weakens, the simulations actually indicate that the hold of El Nino on the Indian Ocean realm also weakens. And so that allows the Indian Ocean dipole and this equatorial mode to emerge in the Indian Ocean and really dominate the SST variability, and which is much more increased relative to today. In the future, we're uncertain about what ENSO is going to do, and ENSO is really a key sort of thing that we need to pin down for regional climate evolution. But what we can really say in terms of stability or not is that ENSO serves to sort of impact the monsoons in the forthcoming year, and this mode seems to impact the monsoons during that particular year itself. So whatever it's going to be, we need to further investigate the exact sort of relationship between the two. But that said, we know that both of them together are going to impose more uncertainty in their evolution and furthermore on their impacts for hydroclimate across the Indian Ocean realm as well as Asia.
Okay, well, thank you very much again, Kyle. I think that's probably all we have time for. There are a couple more questions in the Q&A, so please do check that out as we go through the next talk. So I think now we have the 1 minute pre-recorded talk. So Alicia, are you able to press play on those?
We sampled South African rivers and isolated the finest grain size fraction. This clay fraction has the highest potential to integrate the river catchments into the marine realm, as this fraction is more easily transported than coarser fractions. We find 3 M members explain 89% of the variance in the grain size data, and additional M members added are in the coarse fraction. When compared with typical marine M members from the Southeast African continental margin, M member 3 from the river data fits better with M member 2 from the marine data. We analysed clay minerals and radiogenic isotopes from this isolated clay fraction to minimise the strontium grain size offset. We noticed that Karoo supergroup samples have a younger strontium fingerprint than the Cape supergroup beyond analytical error, and we hope to constrain the provenance of these river sediments by coupling the clay mineralogy and using neodymium strontium ratios, as neodymium is less sensitive to grain size. If you have any questions, please come to my breakout room. Thank you.
Hi, My name is Tom Rachael. Let me tell you about our poster on Eocene plant fossils from Australia and what they can tell us about climate and primary productivity in the ancient land down under. Plant fossils reveal environmental conditions through morphological characteristics as well as taxonomic affinities. We combined plant paleoclimate proxies for 12 localities to reveal early to middle Eocene temperature, rainfall, and net primary productivity. In the present day, there is rainforest along the Australian east coast. These forests have high rainfall and primary productivity, especially in the tropics. During the Eocene, when Australia was situated 30 degrees further south, temperatures were uniformly subtropical. Rainfall is higher at sites that are closer to the coast, but inland sites experience at least 4 to 5 times as much rainfall as they would today. Accordingly, the net primary productivity was uniformly high as well, similar to subtropical forests today. This is in stark contrast with the large areas of grassland and deserts on the Australian continent, where net primary productivity is close to zero today, and implies a greener continent down under during the early to middle Eocene.
Hi, I'm Marcy Robinson in my backyard in Fairfax, Virginia, and I'd like you to come take a look at my poster on paleoclimate signals in the coastal plain sediments. We've looked at coastal plain sediment cores and outcrops from the eastern parts of Virginia and Maryland along the mid-Atlantic coastal plain of the United States, and we've looked for sediments from 3 warm periods when sea level was high compared to today and marine sediments were deposited on today's coastal plain. The Paleocene Eocene thermal maximum, the Miocene climate optimum, and the mid-Piacenzian warm period. In short, we found that these sediments contain excellent snapshots of extreme climate states and record valuable quantitative paleoecological data. This work is important because these records capture the nature of climate-induced changes in this area where a lot of people live, and it highlights the differences within a single warm interval that might have multiple pulses of sea level. And all of this leads to a better understanding of potential future impacts. So come take a look at my poster and feel free to ask me questions. Thank you.
Hi everyone, welcome to our talk on the tectonic and glaciostatic sea level reconstruction for the entire Phanerozoic. These are our ice estimates through time. In solid blue, we have our 1 million year steps reconstruction of a land ice volume. And in the dotted lines, we have our ice volumes both for glacials and interglacials. So these are the peaks of ice variation that we estimate that could have happened within or less than 1 million years. So you can see, for example, in the late Paleozoic ice house, there was a lot of variation in land ice volume. And as a consequence, this leads to a large variation in sea level too. When we combine our sea level curves with a stratigraphic estimate from a compilation of studies of Huck, you can see there's a lot of similarities at first order level in the Mesozoic and Cenozoic, but to a lesser extent we're in a lesser agreement for the Paleozoic, which we need to research further.
Hi, I'm Tom Gernon and I want to talk to you about mobilization of mantle carbon during the PTM. So some recent studies have implicated the North Atlantic igneous province in driving PTM warming. However, using plate simulations, we calculate that ocean ridges and large igneous provinces at this time yield only about 1/5 of the carbon required to drive that warming. Instead, we identified volcanic sequences spanning the PTM that showed geochemical evidence for substantial increases in mantle melting at this time, which involved metasomatized lithosphere, which is a key reservoir of carbonate. Using coupled tectonic geochemical models, we show that this process is melting can drive over 10,000 gigatons of carbon being released, which is sufficient to promote PTM warming. We propose that enhanced melting of the cratonic lithosphere during stretching causes a 5-fold increase in volcanic carbon release, driving the PTM and reconciling a deficit of carbon from background ridge and lip magmatism.
Hello. The Southern Hemisphere westerly winds have long been hypothesized to help regulate atmospheric CO2 over glacial interglacial cycles. However, constraints on past changes in the winds are lacking. Here we exploit the link between the position of the sea surface temperature front in the Southern Ocean and the position of the westerlies, and using a compilation of planktic foraminiferal delta 18O and an ensemble of climate models, we reconstruct shifts in the winds over the last deglaciation. We find the westerly winds were 5 degrees equatorward during the LGM compared to the mid-Holocene and about 25% weaker. We show the poleward shift in the westerly winds over deglaciation closely mirrors the rise in atmospheric CO2. Using a 1/4 degree resolution ocean carbon cycle model, we show that shifting the westerlies equatorward slows the circulation of the abyssal ocean, increasing oceanic carbon storage. Our findings suggest a central role for the westerlies in driving the deglacial rise in CO2.
IPCC says the sun plays almost no role in climate change. Let's see if we agree. Which two curves correlate best? Yes, the first two. The sun's magnetic output and global temperature strongly correlate visually for the last 2,000 years, with a 100-year temperature lag. And what's this solar surge from 1700 AD? It's the largest rise and the strongest grand maximum in more than 10,000 years. Look at the multiple matches between the sun's magnetic output and global temperature since 2,000 years ago. I conclude that the sun's modern magnetic surge, combined with ocean lag, can explain 100% of modern warming by Svensmark's theory. Has an overlooked feedback cancelled CO2's greenhouse effect?
The polar ice cores show cyclical temperature changes dominated by the Earth's 3 orbital cycles. The carbon dioxide cycles show a lag behind temperatures, particularly in the cooling phase. The influence of 7 solar cycles has long been recognized by scientists. The 7 major ones were also identified on a 700,000-year-long section of Eocene sediments in Lake Messel. A synthesis of these 7 cycles shows a close correlation with the measured values. It is clear, therefore, that global temperature changes can be related to persistent changes in energy arriving from the sun, and that carbon dioxide has little effect on climate.
Hello, my name is Benjamin Petrick. Here you see the title of my poster and my co-authors. I'm today going to talk to you about new records I developed from the Western Australia. The record I developed is here in red, and I'll talk more to you if you come to my poster about the connections, but essentially we found one cooling around 1.6 million years and one cooling at 600,000 years. We think these coolings are a result of changes in water level due to sea level changes in the Indonesian through flow, and that these changes had impacts on the climate of the local area and global circulation. So come to my poster and I'll say...
Hello, I'm Brian Catt. As a practical physicist, my approach contrasts the observable physics of climate with the predictions of models in 3 ways. Earth's climate changes continually on multiple natural frequencies. Change is normal. Recent change reflects the natural cycles and shows no industrial warming anomaly. Climate is very stable, strongly controlled within a narrow range by evaporative and cloud albedo response to ocean warming, with no catastrophic tipping points. The atmospheric lapse rate, hence surface temperature, is primarily controlled by solar surface heating plus gravitational pressure in Maxwell's convective equilibrium. The radiative greenhouse effect on this is very small, mostly natural and from water vapour, and the control reverses change. Change is real, but CO2 is not significant within it. The sun heats, the oceans control, the cycles repeat. Civilization is hugely successful in using its economic progress to protect itself against nature. But the UN plan to restrict Western energy use, hence progress. They employ models that attribute natural change to CO2, then predict on this presumption as if proven. Direct and proxy observations since 2000 have serially disproven this causal relationship. So I suggest truly scientific bodies should prepare the evidence of nature to the presumptions and models in this matter. Thank you.
Howard Dewhurst. I present observations that contradict the basic tenets of the AGW conjecture and will explain why human emissions do not drive climate change. The increase in atmospheric CO2 of 94 parts per million since 1965 is only partly due to the 185 parts per million added by humanity. The year-on-year changes in atmospheric CO2 are up to 2 orders of magnitude larger than emissions. Cutting them will not remove natural variability. The correlation of global sea surface temperatures and lagged atmospheric CO2 indicates that global temperatures and not human emissions drive atmospheric CO2. The claim that the global carbon budget was balanced before human emissions began is an unsupported assumption, not a fact. This does not mean that emissions have no effect, but it does mean that they control neither global warming, a measurable quantity, nor climate change, which has no units. Both are symptoms of climate change, not causes. A conjecture supported by a recent lab experiment that found that an atmosphere of 100% CO2 caused no more warming than one with 0.04%. This experiment will not be the last word, however, because the science is never settled.
This paper investigates inconsistencies post-LIA between physical observations and climate models and forcings. Surface temperatures and models agree warming commences around 1910 and that 2 periods of warming are evident, early and late 20th century. The observed temperature, glacier and sea level data agree the ratio of these 2 warming rates is about 1.4 times. However, climate model input forcings and output temperatures have ratios that are more than 2 times larger. Sea level and glacier retreat data show the onset of warming post-LIA commences much earlier, around 1840, with a 3rd warming period evident in the 19th century. Here we also note climate model residuals are structured and periodic. Comparing the 3 warming periods, we note the rate of glacial retreat is similar for all 3, with the most recent warming period statistically the slowest rate of retreat.
The geological community should be included in the climate debate. The last interglacial, the Eocene, which started 135,000 years ago, was far warmer than today's, yet CO2 parts per million were far lower. In the intervening years, ice sheets reached the Scilly Isles. Montreal was under 3 kilometers of ice. It all melted at far lower CO2 ppm levels than we experience today. We know it was warmer from ice core data, from floral and faunal records. Hippopotamuses, for instance, and other tropical and subtropical creatures roamed the higher latitudes. Before taking down Western society, we need to re-examine Tyndall's 1859 experiment and assertions, as the relationship between CO2 and temperature is logarithmic and not linear. The modest temperature rise we are experiencing right now is normal. Thank you for my minute, and yours.
Hi everyone, my name is Amy Jewell and I'm a final year PhD student in the Paleoclimate Research Group here at Southampton. So North Africa produces about 50% of Earth's dust, and this dust accumulates in marine sediments in the North Atlantic, providing us with a continuous archive of continental aridity. I've been using strontium and neodymium isotopes at ODP Site 662 to establish the provenance of the lesser studied winter dust route and how this has changed through the Quaternary. So in my poster presentation, I will explain how we geochemically characterize 3 distinct North African preferential dust source areas, and then we use this to establish that there are 2 geochemically distinct routes of dust transport off North Africa, enabling us to study regional climate change. And then finally, I demonstrate how the winter dust route can be used to track the paleohistory of the dustiest place on Earth, the Bodélie Depression, and the surrounding Paleo Lake megachat. Thanks so much, and I'd be delighted to hear any comments or questions in the poster session.
Hi everyone, my name is Gordon Ingalls from the University of Southampton. I will be presenting a recent study looking at the operation of the terrestrial methane cycle during the Paleocene-Eocene thermal maximum 56 million years ago. In this study, we use a novel biomarker-based approach to reconstruct methane cycling within a high latitude wetland. We show that the methane cycle was intensified relative to the modern. And for the first time, we show that the onset of rapid warming during the PTM is particularly crucial for modifying wetland biogeochemical feedbacks in Earth's history. So if you want to find out more, you can come find me in the poster session soon.
The sedimentary succession of the Helmstedt lignite mining district in northern Germany covers the entire Paleogene greenhouse phase and its gentle demise almost continuously from the latest Paleocene to the middle Eocene, including the early Eocene climatic optimum and some short-term warming events such as the Paleocene-Eocene thermal maximum. And the more than 200-meter thick section has been deposited in an estuarine setting at the southern margin of the Proto-North Sea. The aim of an ongoing project is to study the response of the vegetation in this paralic environment to the long and short-term thermal events by making use of pollen and spores as proxies. And here we present a new stratigraphic framework for the succession, which allows for an exact identification of individual Paleogene thermal events. Now it is possible to reconstruct the vegetation for times before, during, and after specific thermal events.
Hello, this is Valeria Luciani speaking. At the poster session, I will talk about the impact of the early Eocene climatic optimum on plantic foraminiferal assemblages. These are the sites investigated from the Atlantic to the Pacific Ocean. And a first major change is a turnover between the genera Morosovella and Carinina. And precisely, the genus Morosovella permanently and markedly declined at the beginning of the eco, close to the J event, and the genus Carinina increased in abundance and diversity. A second major change is a switch in the Morosovella coiling direction from predominantly dextral to sinistral within the eco, close to the key X event. And finally, a third major change involved the genus Chilobumbellina that is known to live within the oxygen minimum zone. And this genus disappeared close to the key X event. Of course, we will talk about the causes and the scenario related to these observed changes.
Hi everybody, I'm Alan Mancini from the University of Turin, and here I present some ideas regarding how we can predict future impact on the Mediterranean region using the geological records. We know that the time in which we are living is characterized by strong anthropogenic pressure, which is impacting the ecosystem, especially the marine one. Among the others, global warming represents a major issue. In the last decades, an increase in the Mediterranean sea surface temperatures was recorded and predict to further increase during the next future. This is happening along with the spreading of the hypoxic zone and a weakening of the thermoline circulation. The evolution of these processes and their impacts are hard to predict. This is the reason why I try to construct past impacts, reconstructing the environmental dynamics occurring during the cyclical Messinian warming phases, with the aim to indicate possible future impact on the Mediterranean region. Thank you for your attention and enjoy the presentation.
My name is Matthew Status, and I am a Masters by Research student here at the University of Edinburgh. Historically, the Chicxulub impact has been widely implicated as the main driver of the Cretaceous Paleogene mass extinction, with the exact environmental impacts of preceding Deccan-Trap volcanism requiring further research focus. Although a causal link between Deccan volcanism and the late Maastrichtian warming event has been made, no other acidification proxies has been generated for this interval. We have generated novel benthic boron calcium trace element analyses which aim to quantify the changes in carbonate chemistry during this hypothermal event. Our preliminary data from ODP 1262 show a decrease of 49.31 micromole per mole towards the peak of this event, suggesting potential ocean acidification caused by Deccan outgassing. If you're interested in learning more, come visit our breakout room on the end of day 2. Thank you.
Hi everyone, in this poster we compile and re-evaluate the best possible CO2 reconstructions from alkanones and boron isotopes. The results of this are discussed in more detail in a paper that's just out in annual reviews, and the key result that comes out is that our best available reconstructions of CO2 are closely coupled with climate. We investigate some of the mechanisms of CO2 change. About 2/3 of Cenozoic CO2 change is explained by changes in ocean chemistry via outgassing and weathering, with the remaining thirds due to changes in the equilibrium constants due to temperature feedback and major ion composition. We place broad constraints on Earth system climate sensitivity, noting the potential for state dependence in climate sensitivity, and we highlight that future energy choices have the potential to send CO2 levels back to those associated with the distant past.
Hi everyone, my name is Asia Watkins and I'm a PhD student studying philosophy of science at Boston University. My poster today is about how to use a process called temporal scaling to compare past and present climate change episodes with the goal of establishing paleoclimate analogues. Temporal scaling is predicated on the observation that rates are not in general independent of the durations over which they are measured. Measuring processes over shorter durations produces systematically higher rates than if these same processes are measured over longer durations. Temporal scaling is often useful in the historical sciences, including paleoclimatology, but also paleontology, geology, and archaeology, because we tend to have data of a lower temporal resolution for processes that happen further back in time. So I look forward to having you join my breakout room to hear more about how temporal scaling works and how we can use it to compare cases of climate change in the geological record to climate change today.
Okay, brilliant. Thank you ever so much for all of those talks. For those of you that are listening and that will be in the breakout rooms later, I look forward to meeting you and talking to you. So our final invited speaker is Rachael James, who is a professor of geochemistry at the University of Southampton here in the UK. Rachael is interested in developing novel chemical and isotopic techniques to improve our understanding of ocean and earth processes, but also to address critical environmental and societal challenges. Today, Rachael is going to be talking about question 9 of our statement. What is the role of geology in dealing with the climate emergency for a sustainable future? So over to you, Rachael. As before, I will turn my video on to give you a 2-minute warning at the end. Over to you.
Thanks very much for that introduction, Charlie. And I'm delighted to be here today and presenting something a little bit different now. So thinking about not so many wiggly lines, but thinking about how geologists can contribute to solving the climate emergency. So this is a plot here of anthropogenic carbon dioxide emissions. And as you're well and truly well versed in now, we can see that anthropogenic carbon dioxide emissions have continued to increase on a sharply upward trajectory since the Industrial Revolution. And there's now extremely strong evidence that this is causing global warming. It's causing warming of the surface oceans. It's changing our weather patterns, and it's causing melting at the poles and hence sea level rise. So in recognition of this, groups of countries have come together to figure out what we can do. And in the 2016 Paris Agreement, it was decided by the global nations that the ambition was to keep the rise in global average temperature to well below 2 degrees centigrade and to pursue efforts to limit the increase to 1.5 degrees. So the question is then, how are we going to do this? Well, the most obvious thing we can do is to stop emissions of greenhouse gases and carbon dioxide. And if we look at this plot here, we can see that we can do this pretty quickly if we transition from an economy based on fossil fuels to renewable energy sources. There's good capacity there to bring down levels of atmospheric carbon dioxide. But you can see that this curve then starts to tail off. And the reason for this, of course, is that some greenhouse gas and some carbon dioxide emissions are hard to avoid. So things like the aviation industry is going to take some time to reduce its reliance on fossil fuels. And other industries such as agriculture are always basically going to be emitting carbon dioxide. So what we can see is by about 2050, we actually need to start not only reducing carbon dioxide emissions, but we need to start actively removing carbon dioxide from the atmosphere if we're going to keep to that 1.5 or 2 degree target. And if we look at projections of what's required, we're going to need to remove on the order of 5 to 20 gigatons, so that's billion tons of carbon dioxide equivalents per year by the end of the century. So what's the role of geology in, first of all, reducing carbon dioxide emissions, and secondly, in removing carbon dioxide from the atmosphere? And that's really going to be the focus of my talk today. So starting with the first of these, the role of geology in preventing carbon dioxide emissions, what we've got to remember is that renewable sources of energy require huge quantities of metals that geologists actually are really good at finding and extracting. So they're things like iron, copper, and aluminium, which we've been utilizing for many thousands of years already. But renewable sources of energy also require other metal resources that may be much, much harder to find. And they include things like rare earth elements, rare metals, including selenium and neodymium. And we need those for photovoltaic panels, and we need them in wind turbines. And we also need the element lithium. And many of you are aware that that's a key component of the batteries for electronic vehicles, but it's also required for batteries for other types of energy storage as well. So lithium is a key topic of research at the moment for finding new resources. And it's been known for some time now, geologists have known that many lithium deposits are associated with subduction zone processes. So that's when the plates come together and subducted by underneath one another. And we also know that lithium is quite often found in what we call post-collisional settings as well, but we still don't really know what the source of lithium in those post-collisional settings is. Is it from lithium in mantle-derived magmas, or is it melting of lithium from lithium-rich sediments? The other key issue is how do geologists can contribute to is how we extract those resources, including lithium, in an environmentally sustainable way. And for those of you who think that geology is kind of an old topic and we never find anything new, I just want to point out that this rather beautiful mineral here, jadeite, that's the light parts that we can see here. It's a lithium sodium borate mineral, and that was actually only discovered in 2004. So those resources are out there. We just need to find more of them. And as geologists as well, we're also increasingly looking to the deep oceans to find new sources of these rare earth elements and other rare metals. And for example, hydrothermal deposits that we find at the sea floor, we get these massive sulfide deposits forming in these hydrothermal settings, and they're a huge resource of copper and zinc. We still don't even really know how much, because a lot of hydrothermal deposits are in fact extinct now and deeply buried under ocean sediments, and we're finding new ways to seismically image those and hence discover them. And some of you may be aware that some companies, for example, Nautilus Minerals, have been developing techniques to mine these sulfides in the deep ocean, so thousands of meters of water depth. In the deep ocean as well, we also have other metal resources. Here I've got some manganese nodules, which are found in the very, very deepest parts of the ocean basins. And they're a big resource of metals such as cobalt, as well as iron and manganese. and the rare earth elements too. And also clay-rich sediments, again, in those deep ocean basins, it turns out that they have extremely high levels of the rare earth elements that are needed for those photovoltaic cells. And the good thing about those is they actually contain much lower levels of unwanted materials, such as uranium, for example, that most rare earth element deposits on land also have high quantities of. Of course, not all mineral deposits are created equally. And this is some work that was done by a PhD student of mine, Amaya Menendez, a few years ago now. And this shows a cross-section through a manganese nodule. This backscatter image here shows regions of high reflectivity, regions of low reflectivity. And if we do some elemental mapping of this manganese nodule, the orange areas here are areas that are high in iron, whereas the purple areas, the pinky purple areas, are areas of the nodule that are high in manganese. And if we look at the rare earth element content of those different iron and manganese-rich regions of the nodules, what we can see is there's a very high correlation between the iron content of those layers within that nodule and the rare earth element content, but not so much of a relationship with manganese. So again, our geological knowledge allows us to really target the areas that are going to contain the highest quantities of the elements that we're most interested in. Another area that geologists can contribute to reducing carbon dioxide emissions is through what we call carbon capture and storage. So this is where carbon dioxide is captured from point sources, so power plants, cement manufacturing, that kind of thing, before it's emitted to the atmosphere, and then is stored in a variety of geological sequences, including spent oil and gas fields under the oceans, unminable coal seams, and also other projects too. And so really, this is sort of the reverse of the resource extraction industry, really. We're reinventing the oil and gas industry. Instead of pulling things out of reservoirs, we're pumping carbon dioxide into them. And the estimated storage capacity in the UK sector of the North Sea is around 78 gigatons of carbon dioxide. And to put that in context, at the 2019 levels of CO2 emissions from the UK, that's about 220 years worth of UK emissions. And obviously, as emissions go down, that period is going to increase. So what then is the role of geology in the other part of my story, which is carbon dioxide removal? And I just want to remind you again, if we go back to those Paris Agreement targets that I discussed in the first slides, we're looking, what do we need to remove? We need to remove about 5 to 20 gigatons of carbon dioxide equivalent per year in order to meet those Paris Agreement targets. So what does this mean? This is a very US-centered image because it comes from a US-based think tank, but it's a gigaton of carbon dioxide is approximately equal to about 9 billion barrels of supercritical carbon dioxide, or twice as much as the US domestic production of oil in 2018. It's equivalent to about 12 times the amount of steel manufactured in the US. And it's also the equivalent of removing the entire light vehicle fleet from the US. So this is a big challenge. So how can geologists contribute to this? Well, I'm sure many of you will know, and you've discussed it. You've all looked at your foraminifera, you've all looked at your carbonate-rich sediments. But carbonates that we see in those sediments and that we see in veins in rocks actually comes from the atmosphere. And so this carbon mineralization, the conversion of carbon dioxide into carbonate rocks, is a natural process that's been going on for since time immemorial. And it's a two-step process. So first of all, it involves the weathering of the rocks by carbonic acid and the conversion of those rocks into divalent cations, so calcium ions and magnesium ions, that are subsequently precipitate as carbonate minerals. And those carbonate minerals securely store that carbon dioxide on timescales of tens to hundreds of thousands of years. So those carbonate minerals are very stable and are an effective mechanism for removing carbon dioxide from the atmosphere. The only issue is this overall process of rock weathering and carbonate formation generally takes time. And remember that we need to start removing significant quantities of atmospheric carbon dioxide by the end of the millennium. So geologists now are looking at ways in which we can speed this up. There are various different ways of doing this, which are summarized on this diagram here. I'm not going to go through all of these today. If you're interested, you can look at this recent report published by the Energy Futures Initiative. But there are different ways that we can try to speed that process up. So one of these then is to take carbon dioxide and inject it into reactive rocks that contain high quantities of calcium and magnesium ions. And this is a project called CarbFix that has been going on for a few years now in Iceland that my colleague Jörg Matter at the University of Southampton is involved in. And what they've done is they've taken carbon dioxide that would normally be released to the atmosphere as part of geothermal processing, and they've injected it into the basaltic rocks that, of course, form the island of Iceland. And the surprising part of the story here, you can see that these carbonate minerals are forming in the voids and vugs within those basalts, is that over 95% of the carbon dioxide that was injected into those basaltic rocks was converted to carbonate within 2 years, so extremely quickly. And the other aspect that I wanted of ways to speed up mineralization process and the weathering process too, that I wanted to talk to you about today, principally because it's an area of active research of mine and my team in Southampton, is carbon dioxide removal via enhanced weathering and mineralization. So remember that that weathering process, so the conversion of atmospheric carbon dioxide into carbonic acid, and then that carbonic acid attacks rocks at the Earth's surface, that naturally removes about 1 gigaton of carbon dioxide per year globally. So the idea to speed this process up is to apply crushed up calcium and magnesium rich rocks to agricultural soils, and then to harness the photosynthetic energy of plants to do the weathering reaction for us. Good thing about this is it's compatible with agricultural practices. Farmers are well used to spreading fertilizers and lime, etc., all over their soils. And there are also potential co-benefits for agriculture as well. So early work on this has mainly focused on modeling. And there was a modeling study that I was involved in, published last year, that you can see here, that suggests that on a global basis, rock weathering in this way could remove about 0.5 to 2 gigatons of carbon dioxide per year if the crushed up rock was applied to 20 to 50% of the cropland area. So they're pretty significant quantities of carbon dioxide, and they're comparable with estimates for carbon dioxide removal via other techniques that you may have heard of, such as BECCS, so that's bioenergy with carbon capture and storage, with direct air capture, and also with nature-based solutions or natural techniques such as afforestation and reforestation. The quantities of carbon dioxide that I'm talking about here are equivalent to more than the current total emissions from global aviation and shipping combined. And the other thing about this technique is that the world's highest emitters, so China, India, and the USA, also have the highest potential for carbon dioxide removal using enhanced rock weathering. And the cost as well is comparable to other proposed carbon dioxide removal strategies. So they're modelling studies. The key is, does this work in practice? So as part of the Leverhulme Centre for Climate Change Mitigation, I'm involved in a series of large-scale field trials in the US, in the UK, in Malaysia, and also in Australia. And today I just wanted to highlight to you some of the results from our trial in the UK, where we have been applying crushed up basaltic rock to peas. This is just an overview of our experimental setup here. So the basalt is applied and ploughed in as usual practice to the surface of the soil. And then we've been sampling the soil pore waters using lysimeters. Okay, these plots are a little bit difficult to see, but along here we have date. And on the top plot here, I'm showing calcium concentrations in those soil pore waters, silicon concentrations, and alkalinity. And what we can see is that in our plot where we apply the basalt compared to our plot which is a control where we don't apply the basalt, concentrations of calcium, silicon, and alkalinity are pretty similar before we stick the basalt in the field. The green line here shows where the seeds were sown. And the growing period extends to here, and then the peas are harvested at this point here, which is 5 months later. And what we can see is that after we've applied the basalt, and particularly after the peas start growing, we see higher levels of calcium in the soil waters, higher concentrations of silica, and higher alkalinity concentrations too. And all of this is evidence for enhanced weathering of the basalt that we apply to those soils, and the higher alkalinity concentrations that we see in these soils equate to drawdown of atmospheric carbon dioxide. And so if we convert those alkalinity concentrations into carbon dioxide removal, I've got cumulative carbon dioxide removal on the vertical axes here. Control plot is shown with the red line, and the blue line, the red line shows the basalt plot and the blue line shows the control plot. And what you can see is over that 5-month field trial, the plot where we added the basalt removed approximately 80% more carbon dioxide than the plot where we didn't apply the basalt. So that's quite an important result. But actually, if we look at the quantities of carbon dioxide that are removed, they're pretty small. And in fact, they're less than 1% of the maximum potential amount of carbon dioxide removal that we would expect given the amount of rock that we added. But one thing I should say is at this site, it's in East Anglia, there are carbonate-rich soils here. We also see evidence for enhanced carbonate precipitation. And that carbonate, of course, also comes from the atmosphere. And that's shown in this plot here. And you can see that the quantities, the change that we see in the amount of soil carbonate that's being produced are really significant, orders of magnitude higher than the change we see in alkalinity. Caveat to this, I would say, is that measurements of soil carbonate are incredibly patchy. We need to do a huge amount of sampling to confirm that this result is statistically significant. And we also need to increase the spatial resolution of that sampling to confirm this. I also mentioned that this technique could have potential co-benefits for the crops themselves. And if we look at the silicon concentrations in the stipular parts of those peas, we can see that they're higher in the plot where we've added basalt. And the higher the quantity of silica in those peas, it makes them more resistant to herbivorous attack. So farmers are happy about this. And there was also a significant reduction in the amount of downy mildew. Now, one question I'm continually being asked when I talk to people about applying these crushed up rocks to crops is, what effect does this have on water quality? Don't these rocks add heavy metals into the water system? Well, actually, in most cases, no, they don't. If we look at aluminium here in the control plot and the basalt plot, actually we see a significant reduction in the amount of aluminium in the soil waters. We see no change in the amount of chromium in those soil waters. And in fact, the only element we do see a change for is the amount of arsenic in those soil waters, which might shock many of you, but I would point out that the arsenic levels that we see here are still 10 times lower than the legal limit. And we think the reason for these changes in metals is, in fact, the secondary minerals that form as a result of weathering of that basalt are mopping up those heavy metals. And the final thing I just wanted to point out for you is that this technique also offers the opportunity for creating a circular economy. In all of those field trials I'm involved in, we're actually using waste products from the mining industry and applying those to the soils. There's potential for creating a circular economy here. And one of my postdocs, Liam Bullock, has done some work on this, where he's looked at the amount of mine tailings being produced on an annual basis, and then looked at the chemical composition of those mine tailings to figure out what their carbon dioxide removal potential is. This would be 10 billion tons, 10 gigatons of carbon dioxide removal per year, and this would be a gigaton here. And on the basis of his work, the types of rocks that are most conducive to carbon dioxide removal are mafic and ultramafic materials, and those that are produced in high quantities by the mining industry. And if we sum that up, those rocks have the potential to capture about 1.4 to 6 gigatons of carbon dioxide per year, which actually could mop up all of that mining industry's primary emissions. Okay, I can see I need to wrap up. It's been a long day. Thank you for staying with us. Points I wanted to make is that geological expertise are vital for mitigating the climate crisis. What geologists can do is identify resources needed for a low carbon society. And they're also hugely important for verifying, quantifying, removal of atmospheric carbon dioxide in geological reservoirs. And those traditional geology industries as well, the oil and gas and the mining industries, can have a really vital role to play in meeting Paris Agreement targets. They operate at significant scale. They're used to doing that. They have the capability of securely storing gas or liquid forms of carbon dioxide, and they have the capability to move and crush vast quantities of material. So I want to wrap up, first of all, by acknowledging all of my colleagues in Southampton, my postdocs, PhD students and collaborators, teams outside of Southampton that I work with, and our funders as well. And I will stop and ask if there are any questions. Thank you.
Thank you ever so much, Rachel. That was absolutely fascinating talk, really, really interesting. So we have a couple of very good questions from the attendees. First up is there a model for how much energy will be required to extract all the additional resources for these new technologies? And what is the CO2 impact of these energy requirements?
Yeah, absolutely. So the modelling study that I referred to in the middle part of my talk takes that into account. So it's not just looking at carbon dioxide drawdown as a result of applying the crushed up silicate rock. It also takes into account the energy required to crush that rock up in the first place, should it not be a waste product, transportation of that material to the site, and all of the knock-on emissions as well. And it still comes out. So the quantities of carbon dioxide that I refer to are net quantities of carbon dioxide that take those processes into account. And the other thing I would say is I'm not in any way advocating that we open up new mines and start crushing up material purely for this reason. That would be crazy.
Okay, so the next question is more about deep sea mining. And it basically asks, could some of the byproducts of deep sea mining, such as detrital carbonates, be used to offset ocean acidification?
For deep sea mining, generally speaking, we wouldn't be mining carbonates because they don't contain sufficient quantities of the resources that we need. We'd principally be looking at hydrothermal sulfides, manganese nodules, and the deep sea clays as well. So we're generally speaking, the resources that we need are not going to be found in the carbonate-rich parts of the ocean. But it is an interesting question that actually has a bearing on the other part of my talk, where I was looking at carbon dioxide removal on land, because actually the weathering part of that process creates alkalinity. And so if those sites are close to the ocean and that alkalinity is transferred to the ocean without the carbonate precipitation process happening, then actually that could partly combat ocean acidification. So alkalinity enhancement as a result of that enhanced weathering process could help to mitigate ocean acidification.
Okay, and I think we've got time for one more question, which is hopefully a hopeful way to end. The question from one of the attendees is, do you think it's possible to reverse many of the negative effects of anthropogenic warming using these large-scale geoengineering projects?
So if they're applied at sufficient scale, there is the potential to lower levels of atmospheric carbon dioxide. I think the only thing, there is no magic bullet here. Okay, none of the techniques I talked about today are magic bullets, and it's going to take a blend of natural techniques such as afforestation, reforestation, blue carbon, so replacing, I'm pointing out here because I'm in Southampton, I could see the ocean today, mangroves, and that kind of thing. It's going to take a blend of all those different technologies. But of course, the massive thing that we need to do is to stop carbon dioxide emissions in the first place. There's absolutely no way that a geoengineering techniques, either by themselves or combined, are going to be any substitute for doing that. That's the most important thing, is reducing emissions. And then the role of these geoengineering techniques is really to mop up that last little bit from those industries that are difficult to decarbonize.
Okay, well, thank you very much again. So this is the end of this session, or rather the end of the invited speakers part. Thank you again to Carl and Rachel, and thank you also to the other speakers earlier on this afternoon. So we now have our breakout rooms. I believe that all attendees will have been sent an email with a link to this. It is a separate Zoom meeting, so it's not this room. And basically the idea is that all these short talks that you heard earlier, they will be there in their own individual breakout room where you can go and chat to them, you can ask questions about their posters, and they can talk to you. The chat room is going to be open any minute, and will be open until 7 p.m. Then we will have a very